discuss about the other new concept which is called the data representation. So data representation we are going to study now. So under this we are going to study about the different concepts which is unsigned and also signed magnitude and the ones complement and the twos complement. All these things that we are going to study one after the another. Unsigned and the signed magnitude and the ones complement and twos complement. So unsigned means here there is nothing like no signed bit. The signed bit is not present. But for the remaining things we are going to use the sign. So therefore MSB is equal to 0 means it is a positive number and MSB is equal to 1 means it is a negative number. So unsigned means there is no signed bit and the remaining all of this remaining three are basically these are signed value means where MSB signed bit is present. So whenever the MSB more significant bit is 0 means it is a positive number and whenever the MSB is equal to 1 means it is a negative number. So all these things we are going to learn in this data representation. So first thing is called as the unsigned and next is called the signed magnitude. The next is ones complement representation and finally twos complement representation. So unsigned representation, signed magnitude representation, ones complement representation and the twos complement representation. So unsigned representation will never have a signed bit. So no signed bit is present. And the remaining three will have signed bits. So particularly MSB if it is 0 it is said to be a positive number and MSB is equal to 1 means it is a negative number. So MSB is equal to 0 means it is a positive number and MSB is equal to 1 means it is a negative number. So now we are going to learn about the unsigned representation for 4-bit. Suppose now we are going to study one after the other. The first case which is unsigned for the 4-bit we are going to study. So unsigned representation for the 4-bit. So you can see clearly the unsigned representation for the 4-bit. Suppose 4-bit means with the help of 4-bit we are going to get to the power of 4 16 combinations. So we are going to get 16 combinations. So 16 by 2 is equal to 8. So first 8 from 0 and next 8 from 1 here. And here 8 means 8 by 2 is equal to 4. So first 4 is equal to 0 then 1. Same repeatedly. So 4 by 2 is equal to 2. So first to make it is 0 then keep 1. So repeat the same process. 2 by 2 is equal to 1. So for each one we are going to represent 0 1 0 1. So like this you have to fill all these things. So therefore we are going to get all these combinations. So you can see basically this is the decimal number is called as this is the decimal number is equal to 0, decimal number 1, decimal number 2, decimal number 3, decimal number 4, decimal number 5, decimal number 6, decimal number 7, decimal number 8, decimal number 9, decimal number 10, decimal number 11, decimal number 12, decimal number 13, decimal number 14 and decimal number 15. So these are the corresponding binary representation for this corresponding decimal numbers. So we can say for 4-bit we are going to represent from 0 number to 15 number. So we are going to represent from 0 number to 15 number and 0 is only one representation. So therefore for n-bit the range is 0 to the power of n and down is -1. 0 to the power of n down is -1. So this is the decimal numbers it can read is the range of decimal numbers it can cover for n-bit. So for n-bit unsigned the range is from 0 to the power of n down is -1 to the power of n -1. So this is the range for decimal numbers it can read. Suppose I now write to you for the 4-bit the range is from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So same thing everything 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So this is the range it can cover. So if you have doubt you can substitute to the power of 4 is 16, 16 minus 1 is 15. Yes, it is covering from 0 to 15 decimal numbers. So this many range it can cover for n is equal to 4. But for generally for n-bit the unsigned representation can cover decimal numbers from 0 to the power of n down is -1. So this is an important point that you always have to keep in mind. So for n-bit, for unsigned representation for n-bit, the range of decimal numbers covers from 0 to the power of n -1. So this is an important point that you always have to keep in mind. So always there is no separate sign bit. Sign bit is not present for this unsigned representation. So there is no specific for there is no sign bit. Sign bit is not present. So now we are going to study about the Another second concept is called as the sign magnitude representation. So using the concept here, sign magnitude representation means, say suppose for positive number, always we are going to keep MSB as 0 and the remaining normal binary representation. So MSB bit we are going to keep it as 0 and the remaining digits we are going to represent the binary representation or remaining normal binary representation is whatever the remaining bits except MSB, whatever the bits that we are remaining, we are going to normally represent the binary representation of the number. So therefore positive means the MSB is always equal to 0 and the remaining bits represent the binary number. So therefore the positive means MSB is equal to 0 and the remaining numbers and the remaining digits are representing the normal binary representation. Negative number means MSB is equal to 1 and the remaining digits are representing the normal binary representation. So this is a very important point that always you need to understand. So for positive means MSB is equal to 0 and the remaining digits are representing the normal binary representation, and negative means MSB is equal to 1 and the remaining digits are representing the normal binary representation. So this is a very important point that you always need to keep in your mind. So positive means MSB is equal to 0 and remaining normal binary representation, and negative means MSB is equal to 1 and remaining normal binary representation. Suppose we will say for the 4-bit sign magnitude. For 4-bit sign magnitude, I will only told you here the input 4-bit we can cover from 0000 to 1111. So we are going to get this sequence. I will only told you you have to go from 0000 to 1111. So now I will only told you the MSB bit is in this one and this is called the MSB bit. So if the MSB is equal to 0, it is said to be a positive number. If the MSB is equal to 1, it is called a negative number. Then this 000 indicates 0 and 0001 is 1, 010 is nothing but 2, 011 is 3 and 100 is 4, 101 is nothing but 5 and 110 is equal to 6 and 111 is equal to 7. But there is a 0 here, so you have to keep it positive. Similarly, here 000 is 0, but there is a 1 here, so you have to keep here. So 001 is 1, but there is a 1 here, so here you have to keep a negative number. 010 is 2, but there is a 1 here, so it is a negative number. 011 is 3, but 1 is there, so it is a negative number. 100 is 4, but there is a 1 here, so it is a negative number. 101 is 5, there is a 1 here, so it is a negative number, minus 5. So this 110 is 6. This is nothing but 1 is called as a minus here. So 111 is 7. Here 1 is a sign, you can sign bit, its 1 is negative. So basically what I am trying to tell you is, if MSB is equal to 0, it is a positive number, and if MSB is equal to 1, it is a negative number, and the remaining digits are going to represent the normal binary representation. So if MSB is equal to 0 means it is a positive number, and MSB is equal to 1 means it is a negative number, and the remaining digits are representing the binary representation. It is going to represent the normal binary representation. So this is a concept that you always need to understand here. So we can say here for 4-bit you can see clearly it is having a range from -7, -6, -5, -4, -3, -2, -1, -0, +7, +6, +5, +4, +3, +2, +1, +0. So we can say it is covering from -7 to, we can say it is covering from -7 to +7, but 0 has 2 representations. You can say +0, -0. So for +0 1 representation, for -1 another representation. So this is the point that we have. So for +0 under 1 representation and -0 has another representation. So 0 has 2 representations in this sign magnitude representation. So this is the point that you always need to understand. So now you can see for n-bit range. So for n-bit, what is the range? I already told you. See, out of 4 bits, we are negating 1 bit. So therefore, now, so therefore you have to remove from n, you have to remove -1. So therefore here, basically it is reading from minus to the power of n minus 1 to plus to the power of n minus 1 minus 1. So this is the important point that you always need to. So this my number of bits, the range for n bit, the range covered is minus to the power of n minus 1 to plus to the power of n minus 1 minus 1, because out of these n bits, one bit we are going to represent for the basically. So we are going to represent for the sign magnitude. The remaining bits that we have to consider minus 1. So therefore, here minus to the power of n minus 1 minus 1 to plus to the power of n minus 1 minus 1. So this is the range of numbers it can represent. So if you want to know for a 4 bit, substitute n is equal to 4. So 2 to the power of 3 is nothing but 8. 8 minus 1 is 7. So minus 7 to plus 7. Yes, it is reading from minus 7 to plus 7. You can see clearly. So it is reading from minus 7 to plus 7. For 4 bit range, it is coming from minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, minus 0, plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6 and plus 7. So I already told you it is coming from minus 7 to plus 7 and the range is from minus to minus 1, minus of to the power of n minus 1 to plus to the power of n minus 1 to minus 1. So minus of to the power of n minus 1 minus 1 to plus to the power of n minus 1 minus 1. So this is the range it can cover for n bit, or we can say for n bit sign negative representation, and 0 has 2 representations in this concept of sign negative representation. MSB is equal to 0 means positive number and MSB is equal to 1 means negative number, and the remaining digits are going to represent the normal binary representation of that number. So this is the point that you always need to understand. So now we are going to study about the one more thing which is called the one's complement representation. I will only tell you one's complement representation, very simple. It is also sign, it is also using the MSB 0 and MSB 1. So MSB 0 means it is a positive number. I will only tell you for positive number it is having the sign bit. So MSB is equal to 0 means it is a positive number and the remaining normal binary representation. It is, and the remaining is normal binary representation, and negative means MSB is equal to 1, and the complement with the remaining above binary representation or write completely the positive number and complement it. So listen carefully. Here, positive number is same as the previous case. The previous sign we have to perform. Same positive number same as this case. But only thing is the remaining number and MSB is equal to 1, and complementing the remaining above binary representation or write completely, write perfectly the positive number and complement it. So basically what I'm trying to say is, so MSB positive means suppose the positive number MSB is equal to 0 and the remaining integers are going to represent that binary representation. So for positive number MSB is equal to 0 and remaining normal binary representation. So for negative number MSB is equal to 1 and complementing the remaining above binary representation or write perfectly the positive number and complement it. So suppose what I am trying to do is, suppose I will explain this concept through this point 4-bit representation. We don't remember this one. So positive means MSB is equal to 0 and the remaining normal binary representation, and negative means MSB is equal to 1 and complementing the remaining above binary representation or write perfectly the positive number and complement it. So now I will explain this concept regarding this one. For 4-bit representation, I will only tell you for 4-bit representation, we are going to the power of 4, 16 combinations. So remember this is MSB bit and this is the MSB bit. MSB 0 means it is a positive number and MSB 1 means it is a negative number by default. So you can see clearly this is MSB. The remaining bits is nothing but 0, 0, 0. It is 0. It is basically 0. 0, 0 is nothing but 0. 0 is a sign bit is 0 means it is a positive 0. So plus 0. And here again 0, 0, 1 means 1. But the sign bit is equal to 0. So it is a positive number plus 1. Suppose here I want to do the I want to find what is the negative number of this one, minus 1. So we want to find what is the minus 1. Simply I have to replace 0 by 1 and I have to complement this bits 1, 1, 0. So we are going to get 1, 1, 1, 0 is nothing but minus 1. So you can see 1, 1, 1, 0 is nothing but minus 1. Same thing I already told you. So therefore suppose for plus 2 you can see here 0 is nothing but positive number plus, and if there is nothing but 0, 0 is equal to plus 2. Suppose if you want minus 2, so what you have to do is here for 0 replace 0 by 1 and complement the remaining bits which is 1, 0, 1. Or simply we can say that write perfectly the positive number and do the complement of it. Inverse is also true. If the reverse complement is also, we are going to get the same one's complement. So therefore, if you write positive number and do complement, we are going to get negative number. Or write perfectly a negative number and do a complement, one's complement, we are going to get the positive number. Now, vice versa is also true. So this is the point that we always have to understand. So now, here MSB is a positive. 0 means positive, plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. So now if you want to write this one, I already told you, so if you do a complement of plus 7, here, we are going to get 1 table 0, it is nothing but minus 7. So if you do the reverse complement also, we are going to get the same. If you do again complement, we are going to get minus 7, plus 7. So if you complement, see, if you complement like plus 7, we got minus 7. If you complement minus 7, then you will get the plus 7. So this is the point that you always need to understand. So this you are going to get minus 6, minus 5, minus 4, minus 3, minus 2, minus 1 and minus 0. So let me tell you again, suppose let me tell you about the minus 3. So you have to get 1, 1, 0, 0. Why it is minus 3 means plus, first you have to go for the plus 3. If you plus 3, 0, 0, 1, 1. To do the complement of this one, we are going to get 1, 1, 0, 0. So 1, 1, 0, 0 is nothing but minus 3. So this is the concept that I am trying to tell you from starting onwards. So always, first thing is you have to get the positive number perfectly and do the complement of that one, you are going to get the negative number. So this is a concept that you always have to understand. So first write that perfectly the positive number and do the complement of that, we are going to get the negative number. Or vice versa is also true. Write perfectly the negative number and do the complement, friends complement, you are going to get the positive number. And vice versa is also true. So finally I can say that positive number means MSB is equal to 0 and remaining normal binary representation. Negative number means MSB is equal to 1 and complementing the remaining above binary representation or write perfectly the positive number and complement it. So this is a concept that you always need to understand. So with the help of 4 bits, we are covering from basically minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, minus 0, plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6 and plus 7. So these numbers we are going to get covered with the help of 4 bit representation, the ones complement representation. So with the help of 4 bits in ones complement representation, these are the range of values we are covering. Suppose for my n bit, same thing, same range as the previous value. For sign magnitude range and the ones complement range is very same, both are identical, which is for n bit range is equal to minus to the power of n minus 1 minus 1 to plus to the power of n minus 1 minus 1. Both are in the same range. You can see clearly sign magnitude and the ones complement representation is same. They have the same amount of range. Same amount of range. So therefore for n bit range, it is for n bit the range is nothing but minus to the power of n minus 1 minus 1 to plus to the power of n minus 1 minus 1 with the help of ones complement. And here also 0 has 2 representations. You can see clearly minus 0 and plus 0. I told you for 4 bit range we are going to get from minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, minus 0, plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6 and plus 7. So these are the range of 4 bits. With the help of 4 bits and with using this ones complement representation, we have the range from minus 7 to plus 7 and 0 has 2 representations. So during addition, if any carry comes, then it is added to again LSB to get the correct result. So basically in this, with the help of ones complement, if you are doing addition, then if any carry comes, then we have to add it to the LSB again to get the correct result. So this is the concept that we always need to understand. So during addition, if any carry comes, then it is added to the again LSB to get the correct result. Suppose if you are using the ones complement representation for doing addition, then during addition, if any carry comes, again you have to add it to the LSB to get the correct result. So during addition, there is this one complement representation. If any carry comes, then it is added again to the LSB to get the correct result. So this is the important point that you always need to understand. So now we are going to study the 2's complement representation. 2's complement representation is nothing but it is also a sign bit representation. So therefore, for positive number, MSB is equal to 0 and remaining bits are normal binary representation. So negative number means MSB is equal to 1 and 2's complementing the above normal binary representation or write perfectly the positive number and 2's complement it. So basically what I am trying to do is same as the previous one. Here, positive number means MSB is equal to 0 and remaining normal binary representation. And negative number means MSB is equal to 1 and 2's complementing the above normal binary representation or write perfectly the positive number and do the 2's complement. So we are going to get the negative number. I will explain this concept with this 4-bit representation. And remember to you, 4-bit representation is nothing that we are going to get to the power of 16 combinations. 16 combinations. Suppose let me take a small example of this one, 0011. So for 0011, I will only tell you in a reversible is nothing but 0 is a positive number, so plus, and the remaining numbers 011, they are going to represent the normal binary representation. So therefore 011 is nothing but 3, so we have to get 3. So this is plus 3. Suppose if you want minus 3, what you have to do is basically, so first you have to write the perfectly positive number you have to write, and then do the 2's complement. So 2's complement is nothing but, so now we have to do the 2's complement of this plus 3. How to do this one? And what I told you, if you want to do the 2's complement, we have to say, we must not do anything up to first line 0. So up to first line 0, we should not do anything. Then after that, we have to do the complement. So you can see clearly, so this is the, you have to always go from this side to this side. So therefore here, this is the first line 0. So after this, you have to do the complement. So therefore this is 1101. Yes, you have seen the 1101. And all you do, see in the 2's complement method, what I'm trying to use basically, see up to first line 0 from, okay, you have to go from here to here. So you have to go from here to this direction. So you have to go from here to here. So up to first line 0, we should not complement anything. After that, we will do the complement. Suppose, let me tell you about this, suppose for plus 6. So therefore this is 0, 0 is, and this 0 is the positive number, and the remaining number are going to represent the binary representation. This is nothing but 1 0 is equal to 6. So this is plus 6. Suppose if you want minus 6, then what you have to do, just do the 2's complement of this number. 2's complement is, you must not do anything up to first line 0. So this is 0, this is 1. So this is the first line 0. After this, you have to do the complement. So this is 0 and 1. So 1 0, 1 0 is minus 6. So you can see 1 0, 1 0 is the minus 6. So this is the concept that we always have to remember. If you want positive number, again do the 2's complement, you are going to get the plus number. So either you do the 2's complement from positive. So if you do the 2's complement of positive number, you are going to get negative number. And if you do the 2's complement of negative number, you are going to get the positive number. So this is a very important point that you always need to understand. So this is the concept that you always need to understand. So therefore, here you can see it is plus 7. So plus 7 is nothing but 0, 1 1 1. So if you want minus 7 and only 12, just do the 2's complement. So this is the first one 0, after that do the complement here. So 1 0 0 1. So 1 0 0 1 is the minus 7. Same thing. Again if you do 2's complement of negative number, it is first one 0. Then you do the complement here. So 0 1 1 1. So this is nothing but plus 7. So 2's complement of positive number is going to give you negative number, and the 2's complement of negative number is going to give you positive number. So this is the important thing that you always need to understand. See, the 2's complement, you can also do it in another fashion. So listen carefully. In another method also you can do. Suppose let me take a small example of 6 number. 6 number is nothing but 0 1 1 0. So 0 is a positive number plus, and here this is nothing but basically it is going to represent the binary representation. This is nothing but plus 6. So this is plus 6. Suppose if you want a negative number, how to do this one? Listen carefully. See, this is to the power of 0, to the power of 1, to the power of 2, to the power of 3. So if we do the simplification, we are going to get to the power of 3 into 0 plus, to the power of 1 into 1 plus, to the power of 1 into 1 plus, to the power of 0 into 0. So we are going to get plus 6. Again here what we have to do basically, here there is a 1. So 1 means always you have to keep the negative. So therefore here negative minus 1 into to the power of 3 is minus 8. Here to the power of 2 into 0 is 0. To the power of 1 into 1 is nothing but we are going to get plus 2, and then minus 8 plus 2 is equal to minus 6. So here 1 means basically it's a minus 1, and 0 means here plus 0. So this is the thing that you always have to understand. So you can do even in this method also, you are going to get the same result. So therefore you can see clearly to the power of 0, to the power of 1, to the power of 2, to the power of 3. Here also to the power of 0, to the power of 1, to the power of 2, to the power of 3. But here it's 1 means you have to keep it minus. So this is what I am trying to tell you. So 1 means here basically you have to keep it minus 1. So minus 1 to 2 to the power of 3 is minus 8 plus 2 1 to the power of 1, just 2. So minus 8 plus 2 is equal to minus 6. Like this also you do. But it is better to remember this concept. Rather than this one, we can remember this one very easier. So 2's complement of positive number is going to give you negative number, and 2's complement of negative number is going to give you positive number. So if you do like this, you are going to get very easier. So finally I can say for positive number MSB is equal to 0, and we need a normal binary representation, and you remember is nothing but MSB is equal to 1, and 2's complement with the normal binary representation, or write perfectly the positive number and do the 2's complement of it, you are going to get the negative number. So the range, suppose you can see with the help of 4 bit. So now you can see with the help of 4 bit the range that we are going to get the data, which is you can see -8, -7, -6, -5, -4, -3, -2, -1, +0, +1, +2, +3, +4, +5, +6 and +7. So like this we are going to get. So we are going to get from -8, -7, -6, -5, -4, -3, -2, -1, +0, +1, +2, +3, +4, +5, +6, +7. So you can see clearly there is only one representation for the 0. You can see clearly there is only one representation for the 0. Suppose for range for n bit. So what is the range for one n bit? See in the previous case, which is minus of to the power of n minus 1 minus 1 to plus of to the power of n minus 1 minus 1. But now here in the this value we will neglect the minus 1. So this minus 1 if you neglect, so you are going to get this expression, which is minus of to the power of n minus 1 to plus of to the power of n minus 1 minus 1. So minus of to the power of n minus 1 to plus to the power of n minus 1 minus 1. So therefore this is the range that we are going to get. So if you substitute n is equal to 4, you are going to get 2 to the power of 3 is nothing but 8. So -8 to +1 we are going to get. So for range for 4 bit is -8, -7, -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7. So this is the concept that we always have to understand. So 0 has only one representation. So therefore I already told you for unsigned representation, for unsigned the range is from, I already told you for unsigned the range is from 0 to 2 to the power of n minus 1. Whereas for sign magnitude, whereas for sign magnitude, we are going to get the representation from a value to the minus of 2 to the power of n minus 1 to plus of to the power of n minus 1 minus 1. Whereas for one complement is also same, minus of to the power of n minus 1 to plus of to the power of n minus 1 minus 1. Whereas for 2's complement representation, the range is from minus of to the power of n minus 1 to plus of to the power of n minus 1 minus 1. So in the sign magnitude and also in the 1's complement, 0 has 2 representation, whereas for the 2's complement, 0 has only 1 representation. So this is the concept that we always have to understand. So if you take 2 bits in the range and if you add, the result is in the range, then it shows correct. If it is not in range, then it shows wrong. So increase the size. So what I am trying to tell you is very simple. So what I am trying to tell you is very simple. If you take 2 bits in the range and if you add, the result is in range, then it shows correct. If it is not in range, then it shows wrong. So increase the size. Suppose if you take any 2 bits, in the range and if you do addition, if the resultant is also in the range, then you are going to get the correct result. But if it is outside the range, then you are going to get the wrong result. Then you have to increase the number of bits to cover that range also. So therefore, if you take 2 bits in the range and if you add, the result is in range, then it shows the correct. If it is not in the range, then it shows wrong. So increase the size. That is the only thing that you can do. Suppose if you take any 2 bits in the range and if you do addition, if the result is also in the range, then whatever the result you are going to get is correct. But if it is outside the range, then you have to increase the range, because whatever the result you are going to get, that is the wrong result. So therefore you have to increase the size. So if you take 2 bits in the range and if you add, the resultant is in the range, then it shows correct. If it is not in the range, then it shows wrong. So better to increase the size. So in 2's complement addition, always discard the carry. So in 2's complement, I already told you, see the 2's complement addition, always you have discard the carry. So whatever the carry that you are going to get to keep by using the 2's complement addition, you have to always discard the carry. So in the 2's complement addition, whatever the result that you are going to get, always you have to discard the carry. So in 2's complement addition, always you have discard the carry. Suppose see clearly here, suppose a small concept. Suppose 0 plus 0. Suppose if you are going to get a 1. Suppose you are going to get a 1. So this is sign bit. This is also sign bit. So two sign bits are positive. If positive and positive, then definitely you should get a positive. But if you got some 1, if you got some negative number, then you will see what is going to happen. And again, similarly, suppose a negative number and negative number. If you add, definitely you are going to get negative number. Suppose in case if you got a positive number. So basically this box indicates these are the sign bits. So 0 is positive number, 0 is positive number. If you have two positive numbers, in case if you are going to get a negative number, means the sign value should be 1. So therefore we can say that. Or if you add two negative numbers and if you get a positive number, means compulsory overflow is occurred. Means overflow is nothing but some error is occurred. So this is the point that you always have to understand. So then compulsory overflow is occurred. So if you do addition of two positive numbers, then definitely you need to get a positive number, but if you got a negative number, means an overflow is occurred, some error is occurred. Similarly, if you have two negative numbers and if you are going to get a positive number, then also it indicates that some error is occurred or some compulsory overflow is occurred. Then compulsory overflow error is occurred. So this is the point that you always have to understand. The addition of two positive numbers, if it is going to give you a negative number, then definitely we can say an error is occurred or overflow is occurred. Similarly, addition of two negative numbers, if you are going to get a positive number, then compulsory means an overflow is occurred or some error is occurred. So these are the 0 means these are basically sign bits. These are basically sign bits. 0 means positive number and 1 means negative number. So this is the point that you always need to understand. So whenever it is happening like this means some error is occurred or some compulsory overflow is occurred. So here another concept, listen carefully. Suppose this is the MSB bits. So we are adding that to MSB bits. This is a large amount of data, but I am considering only the MSB bits. So basically there are some 2 bits of we can say like n bit. Suppose this is a adding 4 bits and B of 4 bits, but I am considering only the MSB bits of A and B. Then we can say clearly, if suppose CIN is coming here and C input is going out from here. Suppose if CIN is equal to C out, means there is no overflow. Overflow is not occurred, means no error. No error. Suppose if CIN is not equal to C out, means you can say yes, overflow is occurred, means some error is occurred. So listen carefully. If both are same, if input carry and output carry, so this is the input carry to this and this is output carry. If input carry is equal to output carry, means no error, or simply we can say no overflow. If both are not equal means definitely you are going to get some error, or you can say some overflow is occurred. So this is the important that you always have to understand. See, whenever the input carry and output carry are equal means there is no overflow. No overflow means no error. And if input carry is not equal to output carry means definitely some error is occurred or some overflow is occurred. So this is what I am trying to tell you. So whenever the input carry is equal to output carry means no overflow. No overflow means no error. And what the result is correct result. Suppose if you are going to do if C is not equal to C out means some error is occurred. So definitely overflow is occurred, means some error is occurred. So therefore we are going to get result like this. By adding two positive numbers you are going to get negative number. By adding two negative numbers you are going to get a positive number. So this is the concept behind this one. I am going to give a summary of all this representation. So different types of representation we are going to see here. Unsigned means here there is nothing like, there is no separate sign bit. For signed and one's complement representation, two's complement representation will be submitted there like the sign bit. So for unsigned we are going to have a range from, for n bit we are going to have range from 0 to the power of n minus 1. Similarly for sign magnitude, the range is covered from minus to the power of n minus 1 to plus of to the power of n minus 1 minus 1. Similarly for Bell's complement, we have a range from minus of to the power of n minus 1 minus 1 to plus of to the power of n minus 1 minus 1. Similarly for 2's complement, just remove this minus 1, so we are going to get this one, minus of to the power of n minus 1 to plus of to the power of n minus 1 minus 1. So this is the range we are going to get. And for sign magnitude and 1's complement, we have two representation for the zeros, but here we have only one representation for the zero. And I already told you, unsigned means whatever the total digit is going to represent the binary, all the binary numbers are going to represent the decimal number. For sine 92, for positive means m is b is equal to 0 and negative means m is b is equal to 1. So for positive number m is b is equal to 0 and the remaining thing is normal binary number. Similarly, for negative number m is b is equal to 1 and the remaining is normal binary number. So normally linear representation. But here for one's complement for positive number m is b is equal to 0 and remaining is a normal binary representation, and for negative number m is b is equal to 1 and we have to complement the remaining above normal binary representation or write perfectly the positive number into the one's complement of that one. Similarly for two's complement I already told you for positive number write the m is b is equal to 0 and remaining is normal binary representation. For negative number we have to do like this, very simple, which is first to keep m is b is equal to 1 and two's complement the above remaining two's complement the above normal binary representation or write perfectly the positive number and then do the two's complement. So this is the point that you always need to understand. So this is the range that we are going to get for each and every representation. So these are the range. Out of this one question will definitely ask in any examination. So I recommend you to remember this range. Now we are going to study about the two's complement adder and subtractor. So basically in this method, so you can see clearly two's complement. So with the help of two's complement, we are going to do even the addition and also subtraction. So the circuit is going to do both the functions of addition and also subtraction based on the method of two's complement. So here, one important point is whenever the control signal is equal to 0, it is going to do the a plus b, means it is going to do the addition of the two binary numbers. If the control signal is equal to 1, it is going to do the subtraction of the a minus b. So basically you can see clearly whenever the control is equal to 0, the circuit is going to do basically the binary addition of the two inputs a and b. If control signal is equal to 1, it is going to do the subtraction of the binary signals a and b. So this is the circuit diagram. This is a circuit diagram which is going to do the perform of both the addition operation and also the subtraction operation on this binary signals. Let me assume each having a 4-bit. So there are two inputs of each having a 4-bit, which is 4-bit parallel adder. So you can see clearly this is A0, A1, A2, A3, B0, B1, B2, B3. So here I am going to keep an XOR gate in front of this B, B0, B1, B2, B3. And this common signal I am going to take it to the control signal, and here this is the C0. This is how we can say C0. I have already told you these are the full adders. So definitely these are the full adders. I have already told you. So therefore for the first full adder we are going to give A0, B0 and C0, and for the second full adder we are going to give A1, B1, and the carry of first full adder we are going to give like this. Similarly I will do each and every aspect of this one. So now this is the C0. So now if suppose if the control signal is equal to 0, then what is going to happen? Suppose I have already told you whenever the control signal is equal to 0, then whatever this input same will be on the output also. If this is B0 means here also B0. If this is B1 means here also B1. If this is B2 means here also B2. If this is B3 means here also B3. And this is 0. So now you can see it is going to blindly do the addition of these A0, A1, A2, A3 and B0, B1, B2, B3. So we are going to get basically the output which is S0, S1, S2, S3 is the summation of these two inputs, binary inputs. Suppose if you want the subtraction, A minus B, then you have to give the control signal as 1. So whenever you give the control signal as 1, then this output will be B0 dash, B0 complement, B1 complement, B2 complement and B3 complement. And also there is a C0 is equal to 1. And already told you here A minus B is nothing but simply here A plus of minus B. A plus of minus B is nothing but minus B is the complement of B. So minus B is called as the complement of B. So complement of B plus you have to add one more which is called as a 1. So that is equal to 1. So see, two's complement subtraction is very simple. Two's complement subtraction is very simple. First we have one's complement and then add the 1. Then add the 1. Then we are going to get two's complement. So two's complement is equal to 1's complement plus 1. So we have to add 1 to the least significant digit or the topmost digit. So then we are going to get the two's complement value. So suppose we are going to use, suppose we are given some value of B. So we have minus b. So how to figure out the minus b? Very simple. First thing is here, you have to. So you have to basically first do the 1's complement of b and then add the 1 to the result of this addition of these two things. Then we are going to get this one S0, S1, S2, S3. This is called as the overall result we are going to get. So see basically what I am trying to tell you. So what I am trying to tell you is very simple. See, minus b is the thing that which is first we have to do the complement of the 1's complement of b and then we have to add the 1. If you add like this, then whatever the result that you are going to get, it is basically a 2's complement value. So 2's complement of plus b you are going to get minus b, and if you do the addition of these two things, we are going to get the result which is a subtraction value that we are going to get. So with the help of the circuit, we can do the addition process and also the subtraction process. So whenever the control circuit is equal to 0, this circuit is going to do the addition of a plus b. If this control circuit is equal to 1, it is going to do a subtraction process a minus b. So now we will discuss about the Karnaugh map. Karnaugh map. So basically what is this Karnaugh map is very simple. In this the variables used are, so we are going to use the variables are, so in the Karnaugh map we are going to use the variables are 1 comma 0 comma don't care. So these are the three variables. So these are the three variables which are the 1 comma 0 comma don't care. Only these three variables we are going to use in the Karnaugh map. So basically the basic agenda of using the Karnaugh map is basically to simplify the Boolean expression. So whatever the expression that you are going to get, sometimes it is a very big one. Using the, you can say, the canonical form of SOP or POS, both are very basically large equations. So we need to simplify them. So in order to simplify them, we have to use the Karnaugh map. So in this, what are the variables that we are going to choose is either 1 comma 0 comma 20. Only these three things that we are going to use in this Karnaugh map. So now we will discuss each and aspect of the Karnaugh map. Suppose for two variables, we have a and b. So this is 0, this is 1. This is 0, this is 1. 0 means a1, 1 means a. 0 means b1, b means 1 means b. So 0, 0 means 0, 0, 1 means 1, 1, 0 means 2, 1, 1 means 3. So this is decimal. We can say 0, 0 decimal representation is 0. For 0, decimal representation is 1. For 1, 0, the decimal representation is 2. And 1, 1, the decimal representation is 3. So 0, 1, 2, 3. So these are the cells for the corresponding min terms and max, min terms and the max terms you can keep here. So in 0, 1, 2 and 3. So this is the point that you always need to keep in your mind. So A is called as the MSB and B is called as the LSB. So this is the important point that you always have to keep in your mind. A is the MSB bit and B is the LSB bit. Suppose, see, I have already told you with the help of two variables we are going to get two square 4 combinations. Here we have 4 cells. So now we go for the three variables. So see, basically in these two variables, let me tell you how to do the, how to do the grouping. So you have to do only the adjacent cells. Only thing that you have to do only the adjacent cells. So these two cells you can do grouping, these two cells you can grouping, these two cells you can grouping. But you can't do like this. You can't do the cells in a diagonally. You can't do the cells diagonally. Only adjacent way that you can group the cells. Either this way you can group them, either this way you can group them, either this way you can group them, or either this way you can group them. Or you can't do the grouping in the adjacent manner. You can't do a grouping in this diagonal manner. Only you can do in the adjacent manner. So this is the point that you always have to keep in your mind. So now we discuss about the three variables. Suppose there are three variables like A, B and C. So with the help of three variables, to the power of 3, we are going to get 8 combinations. Means we need to get 8 cells. So A, B, C. A is the MSB, A is the MSB and C is the LSB. So this is 0, 1. This is 0, 0, 0, 1, 1, 1, 1, 0. So you see clearly, with respect to adjacent, only one variable should change. With respect to adjacent, only one variable should change. So you can see clearly, if 0 is changed to 1, only 1 is the variable. Similarly, these two adjacent cells, only 1 is the variable, means only one variable should be variable should be constant. So this is 1, 1, this is 0, 1. So only 0 is changed to 1. Similarly, for these two adjacent cells, only one variable should change, the other variable should be constant. So 1, 1, 1, 0 means 1 is a constant, but 1 is changed to 0. So only this is changed. So we can say clearly, see, always adjacent cells will have only one variable changing, only one variable they should change. So what I am trying to say is, the adjacent cells will change only by one variable. The adjacent cells are going to change only by one variable. It's a very important point. The adjacent cells are going to change by only one variable. So now if you go for this 0, 0, 0, we are going to get 0. 0, 0, 1 means we are going to get 1. 0, 1, 1 means 3. 0, 1, 0 means 2. 1, 0, 0 means 4. 1, 0, 1 means 5. 1, 1, 1 means 7. 1, 1, 0 means 6. So 0, 1, 2, 3, 4, 5, 6, 7. So 0, 1, 2, 3, 4, 5, 6, 7. So this is the way that we are going to do this one. So any two adjacent cells will have only one variable as variable and the remaining variables are constant. So this is the point that you always have to keep in your mind. So 0, 1, 2, 3, 4, 5, 6, 7. See, only adjacent cells we can group. Only adjacent cells we are going to group because there only one variable is changing. And always you have to group from, see, the highest to lowest. So always you have to group like 8 cells, 4 cells, like 2 cells. We can only group like this, 8 cells, 4 cells and the 2 cells. You have to always try to group from maximum cells to minimum cells, like 8 cells, 4 cells and the 2 cells. So like this that you always have to remember. Suppose now if you have 4 variables, like A, B, C, D. So out of this, A is the MSB bit and D is the LSB bit. So with the help of 4 variables, we are going to get to the power of 4, 16 combinations. So 16 cells we are going to get. So now I am going to draw the Karnaugh map. So this is AB, this is CD. So 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. See, what I am trying to do is very simple. These corresponding, we are going to get 0, 0, 0, 0 means 0. 0, 0, 0, 1 means 1. 0, 0, 1, 1 means 3. 0, 0, 1, 0 means 2. 0, 1, 0, 0 means 4. 0, 1, 0, 1 means 5. 0, 1, 1 means 7. 0, 1, 1, 0 means 6. 1, 1, 0 means 12. 1, 1, 0, 1 means 13. 1, 1, 1 means 15. 1, 1, 1, 0 means 14. 1, 0, 0, 0 means 8. 1, 0, 0, 1 means 9. 1, 0, 1, 1 means 11. 1, 0, 1, 0 means 10. So you can see clearly these are the corresponding terms of maximum terms in the form of decimal values. We are going to get these values. So if you see clearly, the two adjacent cells are being changed by only one variable and the remaining variables are always constant. And also you can see clearly this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is the way that you have to do the marking for the corresponding cells. So this is the way that you always have to keep in your mind. Always we have to group from maximum cells to minimum cells like 8 cells, 4 cells, 2 cells. So like that we have to always do these things. So now we go for the 5 variables. Suppose if we go for the 5 variables, we can say clearly 5 variables means here, let me assume A is called as the max term and E is called as the min term. So A, B, C, D, E. 5 variables means A, B, C, D, E. So initially we are going to get 0. 0 means A bar, 1 means A. So therefore now this is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So now if you write the corresponding min terms, means if you write the corresponding decimal values, then we are going to get this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So this is the corresponding decimal values we are going to get. So from this we have to fill the corresponding zeros and ones, and then we have to group from the maximum values to the minimum values. So this is a key point that you always have to keep in your mind. Always you have to group from maximum values to minimum values, like 8 cells, 4 cells, 2 cells, like that you have to always do this one. If you do like this, you are going to get the answers in a very easier manner. So always the position cells will only vary by only one factor or only by one variable. So this is the point that you always have to keep in your mind. So now some important points regarding the Karnaugh map is implicants. Implicants means each individual term, one is called as the implicant. So each and every term, so each and individual term in the Karnaugh map is called as an implicant. So each and individual term, one is called as an implicant. So you can see clearly, suppose each and individual term, so each and individual term in a Karnaugh map is called as the implicant. So each and every individual term in each and every individual term in a Karnaugh map is called as the implicant. It is called as the implicant means, suppose if you are going to write the SOP means for one, we are going to write the expression. So if you write the, for each individual one, if you write the expression, it is called as an implicant. So each individual term is called as a implicant. So for a given output, we are going to get sum of products. So what are the terms that are present in the sum of products? Each and every term is called as an implicant. So now next comes the prime implicant. Prime implicant means combining cells in maximum way. So resultant term is called as a prime implicant. Suppose if you do the, I already told you, we have to combine the cells from maximum to minimum. So if you do a combination of a maximum, then definitely you are going to get certain simplified answer. That simplified answer is called as a prime implicant. So that simplified answer is called as a prime implicant. So if you group the cells in a maximum way, you are going to get a certain expression. That expression is called as a prime implicant. So combining cells in maximum way, so resultant term is called as the prime implicant. So for a given Karnaugh map, if you put the cells in a maximum way, you are going to get a simplified expression. That simplified expression is called as a prime implicant. And essential prime implicant means if at least one cell is not mapped with any other cells. Suppose if you are mapping certain ones in a Karnaugh map, if you map at one, say at least one cell is not mapped by any other cell except that cell, then the expression is called as the essential prime implicant. So listen carefully. Suppose you are grouping certain cells in a Karnaugh map. Then suppose let me assume I am going to group 4 number of cells with the help of Karnaugh map. I have grouped the 4 cells. Out of this, 3 cells have been mapped by other graphs also. Other Karnaugh means other groupings also, they are mapped these 3 cells. But extra one cell is not mapped by any other grouping. Then the expression is called as the essential prime implicant. So therefore, in a map, at least one cell is not mapped with any other cell, then we call this as the essential prime implicant. So finally we can say that, see, whatever the expression in the for each and every term of one is called as the implicants. So if you group the basically the maximum, so if you group the cells in a managing way, and the simplified expression is called as the prime implicant. But if you group in such a manner, so then at least one cell is not paired with any other cell, then that expression is called as the essential prime implicant. So these are the very important points that you always have to keep in your mind. Now let me tell you some important concepts regarding the Karnaugh map. Suppose if I am going to with the to the power of 1 means 2 number of cells. So if I go to 2 cells means I can lost one variable. So one variable can be lost from the expression. Suppose if you are grouping 4 cells means to the power of 2. So 2 variables can be lost. Suppose if I am going to group 8 cells means 2 cube, then I am going to lost 3 variables. Similarly, for general, if I group to the power of n number of cells, then I am going to lost the n variables. So n variables can be lost from the expression. So this is a very important point that you always have to remember. So if you group 2 cells means to the power of 1 means one variable can be lost, can be minimized. And 2 square means 4. If you group 4 cells, we can remove 2 variables. If you group 8 cells means 2 cube, so 3 number of variables can be lost. Similarly, if you group to the power of n number of cells, then we can lost the n variables, means n variables can be easily removed. So this is a point that you always have to keep in your mind regarding the Karnaugh map. So now we are going to learn about the new concept which is called as the multiplexer. So this is a very important concept that you always have to understand regarding the multiplexer. So multiplexer is written carefully here. This is a multiplexer. To the power of n cross 1. So to the power of n indicates the number of inputs. The number of inputs are to the power of n inputs, and the 1 indicates the output. Only one output we are going to get. So we can say it has many inputs but only one output. So it has many inputs but only one output. So to the power of n cross 1 indicates to the power of n indicates it has to the power of n number of inputs, and 1 indicates it has only one output. And this is called as the n dot. I can say this is called as the n control inputs. So these are called as the n control inputs. So this is called as the LSB and this is called as the EMSB. So this is a very important point. N is called as the number of select lines or the control lines, and to the power of n is called as the number of inputs or number of data inputs, and y is called as the output. So always listen carefully. For n number of select lines, we are going to get to the power of n input lines. So we are going to get only one output. So if you see, for a certain combination, out of this only one input line is going to get activated, and that input line is going to pass through the output, and the remaining lines are going to be deactivated. So only that particular input is going to pass through this output. So this is a very important point. See, out of n, for a certain value of select lines, only one input is going to get activated, and that input is going to get passed through this output y. So this is a very important point that you always have to keep in your mind. So only at a certain value of n, only one input is going to get activated, and that input is going to pass through the output. So we can say simply n is called as the number of select lines or the control lines, and to the power of n is called as the number of input lines or called as the data inputs, and y is called as the output. So we have n control lines to the power of n input data and only one output, which is y. So this is a very important expression that you always have to keep in your mind. So to the power of, see, n is called as the number of select lines, to the power of n is called as the number of data inputs, and y is called as the output. So n is called as the number of select lines, and to the power of n is called as the number of data inputs, and y is called as the output. So let me give a simple 2 cross 1. 2 cross 1 means I have only told you to the power of n cross which here n is equal to 1. So n is equal to 1 means we have 2 inputs and 1 output and 1 control input. So 1 control input of select line. So you can see this is I0, this is I1, and this is output y. So 2 cross 1 means we are going to get 2 inputs with a 1 output and for 1 control line. To the power of 1 is 1 control line. So this is a 1 control line. So you can see it like this is a yes. So when s is equal to 0, this input is activated, so output is equal to I naught. Similarly, if S is equal to 1, this input is activated, so Y is equal to I1. So what is the expression? So the output expression Y is equal to S bar into I naught plus S into I1. So this is a very important point. So then Y is equal to S bar into I naught plus S into I1. So this is the expression that you always have to keep in the mind. So Y is equal to S bar into I naught plus S into I1. So this is the output expression that we are going to get here. So now we go for the mux used as a universal gate. So how to use the mux as a universal gate? I have already told you the NAND gate and NOR gate are used as a universal gate because only with that gate we can build any other basic gate that we want. So that is the reason these are called as the universal gate. Similarly, NOR is also called as the universal gate. So now we will discuss why it is called as a universal gate. Because it can represent any other gate that we want. So because of this reason only it is going to use as a universal gate. So now we are going to build the NOT gate. So if you want to build the NOT gate, so with the help of 2 by 1. So this is the 2 inputs, 1 output and 1 control input. So you can see clearly this is the A, this is the A bar, because if A is equal to 0, suppose if A is equal to 0 means this line is activated. So whatever this output is equal to 1, so we are going to get 1 here. Suppose if A is equal to 1, this line is activated. So whatever this input, it passes through this one. So we are going to get 0. So if A is equal to 0, Y is equal to 1. If A is equal to 1, we are going to get Y is equal to 0. So if you want the expression, I already told you, which is very simple. A bar into 1 plus A into 0. So A into 0 is 0. A bar into 1 is nothing but A bar. So Y is equal to A bar. So this is the expression that we are going to get here. So now you can see clearly I am going to represent the NOT gate. So for NOT gate you can see clearly this is the input A and output Y. So if the input is equal to 0, output should be 1. If the input is equal to 1, the output should be 0. So you can see clearly when A is equal to 0, this line is activated. So whatever this input is passing through output, so here it should be 1. So we are here 1. Similarly, when A is equal to 1, this line is activated. So whatever this input is going to pass through output, so it has to be 0. So this is the 0. So for I0 we have to give 1 and for I1 we have to give 0. Then whatever the output is basically which is A bar, it is always A bar. So we are going to get A bar. So now you told me Y is nothing but which is A bar into I0 plus y is equal to a bar into I naught plus a into I1. So if you solve this one, we are going to get this expression which is y is equal to a bar. Similarly, if you want to, so with the help of this, we have built the NOT gate. Suppose if you want to build the OR gate, then what you have to do basically, so we have two inputs A and B, and output is y. So for 0, 0, 0, for 0, 1, 1, for 1, 0, 1, for 1, 1, 1. So this is the expression of a OR gate. So we have to build this one. See, this is the MSB and this is the LSB. So let me take MSB here and LSB here. So therefore, if A is equal to 0, so whenever A is equal to 0, you can see clearly whenever A is equal to 0, if B is 0, Y is 0. If B is 1, Y is 1. Means if A is equal to 0, whatever the B, same we are going to get output. So therefore, you have to give this line to B. Because this line is activated, so whatever this B, same thing will be output Y. Similarly, if A is equal to 1, if A is equal to 1, you can see clearly, if A is equal to 1, if B is equal to 0, output is 1, if B is equal to 1, output is equal to 1. So irrespective of B, always output is equal to 1. So we have to give this as the 1. So if you have to give this value as 1. So now if you do the expression which is I wanted to tell you, the expression A bar into B, A bar into B plus A into 1. So if you solve this one, we are going to get A plus B. So y is equal to A plus B expression that we are going to get. So this is the OR gate that we are going to implement with this 2+1 marks. Suppose if you want to build the AND gate, you can say clearly, so this is the 2+1 marks. So for AND gate, first you have to write the Boolean expression, which is the truth table A, B and Y, two inputs. For 0, 0, we are going to get 0. For 0, 1, we are going to get 0. For 1, 0, we are going to get 0. And for 1, 1, we are going to get 1. So this is the expression of A AND gate. So suppose I am going to take here A as MSB and B as NSB. So when A is equal to 0, when A is equal to 0, this I0 is going to get activated. So when A is equal to 0, if B is equal to 0, Y is equal to 0, if B is equal to 1, Y is equal to 0. So irrespective of B, always Y is equal to 0, so we have to give here 0. If B is equal to 1, this line is activated. So for this combination, we can say if B is equal to 0, Y is equal to 0. If B is equal to 1, Y is equal to 1. So it is following the B. So we have to give here B. So therefore now, if you write the expression which is Y is equal to A bar into 0 plus A into B, you are going to get AB. Y is equal to AB, you are going to get. So you can see this is basically, we are going to implement the AND gate with the help of this circuit. So we are going to build the AND gate with the help of 2+1 box. So now I want to implement the NAND gate with the help of 2 plus 1 box. So same thing here, A, B and Y. So I am going to write the truth table for the NAND gate. For 0, 0, we are going to get 1. For 0, 1, we are going to get 1. For 1, 0, we are going to get 1. For 1, 1, we are going to get 0. So this is the expression, this is the truth table for a NAND gate. So now what I am going to do basically, suppose if A is equal to 0, suppose if A is equal to 0, then if B is equal to 0, Y is equal to 1, if B is equal to 1, Y is equal to 1. So irrespective of B, always we are going to get 1. So here, this I0 is going to get activated for A is equal to 0. For I0 we have to give 1. Similarly, when A is equal to 1, I1 is going to get activated. If B is equal to 0, Y is equal to 1. If B is equal to 1, Y is equal to 0. So it is complement of B. It's a complement of B. So you have to give complement of B here. So now if you simplify, I have already told you Y is equal to A bar into 1 plus A into B bar. You are going to get AB whole bar. We are going to get. So this is the expression that we are going to get, which is AB whole bar. So we can say this is said to be a NAND gate. So now we are going to build the NOR gate. Suppose if we want to build the NOR gate, what we have to do basically here, first you have to write the truth table. It is A, B, Y. For 0, 0 we are going to get 1. For 0, 1 we are going to get 0. For 1, 0 we are going to get 0. For 1, 1 we are going to get 0. So now I want to build the NOR gate. So what I will do basically, when A is equal to 0, we can see clearly I0 is going to get activated. So when A is equal to 0, if B is equal to 0, Y is equal to 1. If B is equal to 1, Y is equal to 0, it is a complement of B. So we have to give a complement of B here. Similarly, if A is equal to 1, I1 is going to get activated. So therefore, if B is equal to 0, Y is equal to 0. If B is equal to 1, Y is equal to 0. Means irrespective of B, always output is equal to 0. So we have to give here 0. Then, if you simplify, I want it to be Y is equal to A bar into B bar plus A into 0. We are going to get A plus B whole bar. So this is called as the NOR gate. So we are going to implement the NOR gate with this circuit. So now I am going to build the XOR gate with the help of 2 cross 1 box. So first thing is you have to write the truth table. So for A, we are going to get output Y. For 0, 0, 0. For 0, 1, 1. For 1, 0, 1. For double 1, we are going to get 0. So XOR means only if the input has odd number of 1s, then only we are going to get output as 1. Otherwise we are going to get output as 0. So now we can see clearly very important point, that is always one important point, which is here. If A is equal to 0, I0 is going to get activated. If B is equal to 0, Y is equal to 0. If B is equal to 1, Y is equal to 1. So whatever may be, same thing we are going to get as output. So we have to give here B. Similarly, for A is equal to 1, I1 is going to get activated. So therefore, when B is equal to 0, Y is equal to 1. If B is equal to 1, Y is equal to 0. It's a complement of B. So we have to get complement of B. So if you simplify, I have already told you, which is A bar into B plus A into B bar. If you solve this one, we are going to get A XOR B. A XOR B is equal to A bar B plus A B bar. So this is the expression that you are going to get. So with the help of the circuit, we are going to implement the XOR gate. So now we are going to build the XNOR gate. So if you are going to build the XNOR gate, so this is the very truth table that you always have to keep in your mind. For AB we are going to get the output as y. For 0 0 we are going to get 1. For 0 1 we are going to get 0. For 1 0 we are going to get 0. For 1 1 we are going to get 1. If a is equal to 0, I0 is going to get activated. If b is equal to 0, y is equal to 1. If b is equal to 1, y is equal to 0. It is a complement of b. So this is a b bar. When a is equal to 1, you can see I1 is getting activated. If b is equal to 0, y is equal to 0. If b is equal to 1, y is equal to 1. So it is equal to b. So whatever the value of b, same thing is output. So we have to give a b. So if it's similar to this one, y is equal to a bar into b bar plus a into b. If you solve this one, we are going to get a x naught b, because a x naught b is equal to ab plus a bar b bar. So this is the expression that we are going to get. So with the help of this way, that we are going to build all the circuits, which is NOT gate, OR gate, AND gate, NAND gate, NOR gate, XOR gate, and XNOR. All these things we can build with the help of MUX. So that is the reason MUX is called as a universal gate. So now we will discuss about the DMUX. DMUX means it is the inverse of the MUX. It is the inverse of the MUX. So you can see now input is only one. Input is only one input, but output we have n number of outputs we are going to get. So in the previous case only to the power of n inputs means only one output, but it is the reverse of the MUX. It is DMUX means input we are going to get only one input, but output we are going to get n, and you can say to the power of n outputs we are going to get. So this is 1 cross to the power of n. So basically the general expression is 1 cross to the power of n. So 1 cross to the power of n means to the power of n outputs we are going to get with only one input. The number of control inputs or select lines are n. So listen carefully. The number of inputs are only 1, and the number of select lines are n, and the number of outputs are to the power of n. So general expression is 1 cross to the power of n. So now suppose basically if I take only 1 cross 2 means 1 cross 2 means one input, two outputs and one select line. Then this input I is given for each and every inside the block, which is, so we are going to get y0, this is y0 and this is y1. Y0 is equal to s bar into I plus n, here is into I. So like this that we are going to get. So for a certain input only, out of all these output lines, only one output line is going to get activated, and that output line will have the whatever this input will pass to that particular output only we are going to get. So listen carefully. For a particular value select input, out of this to the power of n, only one output line is going to get activated, and the remaining things are not going to get activated. So that activated line, whatever the activated line, will have same output as the input. So this is the thing that you always have to keep in your mind. Suppose if you have 1 cross to the power of 2. 1 cross 4 means 1 cross to the power of 2. So we have one input with 4 outputs, and we have 2 select lines or 2 control lines. So you can see clearly this is the input I. So this is S0 S1. S1 is the MSB and S0 is MSB. So we are going to get 4 output lines, y0, y1, y2, y3. So we are going to get like this, which is here 0 0 means S1 bar, S0 bar I. Here 0 1 means basically S1 bar, S0 I, and here 1 0 means it is S1 S0 bar I, and 1 1 means S1 S0 I. So these are the expressions that we are going to get for each and every output. For a certain combination, only one output line is going to get activated, and the output will have the same output as the input. So we can say this is 1 to many. MUX is called as many to 1, and DMUX is called as the 1 to many, because only one input and many outputs. So this is called as the 1 to many. Whereas the MUX has many inputs but one output, so this is called as the many to 1. So this is the point that you always have to keep in your mind. So DMUX is the inverse of the MUX. So now we discuss about the other concept just called as the decoder. So decoder means it converts the binary number system to other number system. So decoder means basically it is converting the binary number system to the other number system. So basically if you take in your laptop, you are going to basically type the letters on your keyboard. So what the computer is doing basically the initial stages first we have the encoder. So encoder converts the normal decimal system to binary system. So then there will be decoder. So decoder is going to basically do the reverse operation which is binary to the other decimal number system, any other number system that we want. So initially in the keyboard we are going to have the decimal number system to binary, and then the computer is going to process the binary system and it has to do decimal. So the output, whatever the output that we are going to see on the screen, it is a decimal format means inside. After that binary operation, you will have a decoder. So it is going to convert the binary to decimal or any other number system. So we can say very simple important point. So encoder is always going to convert the decimal number system to any other number system, is binary number system, and the decoder is going to convert the binary number system to any other number system. So listen carefully. So basically encoder is going to convert the any number system to decimal numbers into binary number system, and decoder is going to convert the decimal number system to any other number system. So finally I can conclude that basically this encoder is going to convert the any other decimal system to binary number system, and decoder is going to convert the binary number system to any other number system. So here we are going to learn about the decoder. So decoder is going to convert the binary number system to any other number system. So this is the decoder. So decoder is basically same as a DMUX. So very important point. So decoder is same as a DMUX, but only thing is here, just we have interchanged the for the DMUX we have interchanged this control inputs here and this input here. So this is an important point. Just we have, so decoder and DMUX is same. Decoder and DMUX is same circuit that we are going to use. We have nothing changed in the circuit. Everything is same, but only thing that we are going to do is here in the DMUX with this input is here and the control inputs are here. So now just we are interchanging the positions. So these are the control inputs and this is the input actually for DMUX. So just we have interchanged this one. So now we can say these are called as the, so for n inputs we are going to get 2 to the power of n outputs. So for 2 inputs we are going to get 2 to the power of 2 which is equal to 4 outputs. So for 2 inputs we are going to get 4 outputs. They one control input. Now this is going to become the control input or enable input. So circuit is same, the DMUX circuit and decoder circuit is same, but only thing is we have interchanged the positions of the control inputs and the inputs. Then we are going to get the decoder. So we can see for any inputs we are going to get to the power of n combinations, but only one control input, or we can say this is called as the enable input. So with the help of this enable switch, either we can just make the circuit to be do the operation or not do the operation. So this is the point that you always have to keep in your mind. So let me take a small example of the general expression of decoder is 2 cross to the power of n. So 2, see, basically n cross n to the power of n. So n cross to the power of n is the general expression of a decoder. So for any inputs we are going to get to the power of n outputs. So general expression is n cross to the power of n. Suppose if n is equal to 2, so 2 cross 2 is equal to 2 cross 4, 2 inputs and 4 outputs we are going to get. So 2 inputs are A and B and 4 outputs we are going to get. And only told you y0, y1, y2, y3. y0 is equal to A bar, B bar, E and A bar, B, E and AB bar, E and ABE, like 0, 0, 0, 1, 1, 0, 1, 1. And this input E is common for each and every block. So we are going to get like this. So y0 is equal to A bar, B bar, E, y1 is equal to A bar, B, E, y2 is equal to A, B bar, E and y3 is equal to A, B, E. So this is the output that we are going to get for each and every thing. So this is the important point. So therefore, for decoder, the general expression is n cross to the power of n. So we have to remember like this. First we have learned about the mux, then we have learned about the demux, and then we have learned about the decoder. So this is the important way that you always have to keep in your mind. So first thing that we have learned about the mux, then we have learned about the demux, and then we have learned about the decoder. And all you told you for mux, the representation, the general representation is 2 to the power of n cross 1, and for demux, the general expression is 1 cross 2 to the power of n, and the general expression of decoder is n cross to the power of n. So these are the points that you always have to keep in your mind. For mux, the general expression is to the power of n cross 1, and for demux, the general expression is, which is 1 cross to the power of n, and for decoder, the general expression is n cross to the power of n. So these are the points that you always have to keep in your mind. So now we are going to learn about the encoder. So encoder is going to convert the other codes into binary. I have already told this important point. So basically encoder is going to convert the any other number system to binary number system, and the decoder is going to convert the binary number system to any other number system. So I have already told you in your laptop you are going to type your keywords. So it is converting any other number system to binary number system, and after doing the operation by computer processing data, it is going to display the output. So when we are going to keep a decoder, it is going to convert the binary number system to any other number system. So this is the important point that you always have to keep in your mind. So finally I can say that encoder is going to convert the any other number system to binary number system, and decoder is going to convert the binary number system to any other number system. So now we are going to learn about the encoder. So encoder is going to convert the any other number system to binary number system. So now you can see clearly ordinary octal to binary encoder. So ordinary octal to binary encoder, we are going to get circuit like this. So you can see clearly. So I want to convert the octal to binary. So now I want to convert the octal to binary. So for octal we are going to get from I0 to I7. So I0, I1, I2, I3, I4, I5, I6 and I7. So now this is the encoder. So we are going to get, see for basically for each and every octal digit we can represent by 3-bit binary. So I0, I1 and I2. So now you have to write the truth table. You have to write the truth table for all these things. I0, I1, I2, I3, I4, I5, I6, I7 and Y0, Y1, Y2. See, if any of this line is activated, if that particular output expression that we are going to get, suppose if 0 is activated, then what is the output we are going to get, which is 0, 0, 0. If 1 is activated, 0, 0, 1. So basically, this Y0 is the LSB and Y2 is the MSB. So you have to write in the reverse fashion. For 0, it is 0, 0, 0. And for 1, 0, 0, 1. For 2, 0, 1, 0. For 3, 0, 1, 1. For 4, 1, 0, 0. For 5, 1, 0, 1. For 6, 1, 1, 0. For 7, 1, 1, 1. So now you have to simplify the Karnaugh map. So you have to simplify the Karnaugh map, and finally you are going to get the circuit. If you build a circuit, you are going to get the Karnaugh map expression, which is I0 is equal to I1 plus I3 plus I5 plus I7, and I1 is equal to I2 plus I3 plus I6 plus I7, and Y2 is equal to I4 plus I5 plus I6 plus I7. So basically this is the OR. So like this that you are going to get if you simplify the Karnaugh map. These are the expressions that you are going to get for the Y2, Y1 and Y0. So you can see clearly this is, suppose at a time if more than one input is activated, suppose at a time if more than one input is activated, then its output will have some expression which does not tell the binary conversion of these inputs. So we can say, suppose at a time, suppose if only one input is activated at any one time, so whatever the output we are going to get is the binary representation of that input. But if you give more than one input activated at a time, so this output is not at all equal to the corresponding binary representation of this input. It is another input, so it is another output that we are going to get. So this is called as that. This is not going to get it, which is out of this which is higher, and that value we are not going to get the binary. So if you want to do that one, we have to go for the priority encoder. See, priority encoder is nothing but, see, out of two inputs, suppose if two inputs are activated, Out of those, whichever is having the highest number, that is going to get priority, and that output is going to get here. We are going to get that particular output that we are going to get. Suppose if 3 and 4 is activated at a certain time, so out of 3 and 4, 4 is having the highest number when compared to 3, so 4 output we are going to get, which is 1, 0, 0. Similarly, suppose if I4 and I7 is activated at the same time, at the one instant I4 and I7 is activated, then the output will have only the output of I7, because the I7 is higher priority than I4, so therefore we are going to get 1, 1, 1. So this is called the priority encoder. So priority is, it is giving priority to the highest digit, and that corresponding binary conversion only we are going to get as the output. Suppose I will go for the, which is I0, I1, I2, I3. Only for these three things, only for these 4 inputs I want to do the conversion. Then if you write the, for 0, for suppose if you write the Karman graph, for I0 is equal to 0, and then is, say, if I0 is equal to 1, and in respect to the other inputs, in respect to the other inputs, we have to get a Karman graph here, output we are going to get 0, 0. Similarly, when I1 is equal to 1, irrespective of the other inputs, let's say, irrespective of this input, irrespective of this input, definitely you have to give output like this. So if you write the Karnaugh graph, and finally if you solve this one, we are going to get y0 is equal to I3 plus I2 bar I1, and y1 is equal to I3 plus I2. So this is a point that you always have to keep in your mind. Suppose if I0 is equal to 1 and this all are 0, then we are going to get 0, 0. Suppose if I1 is equal to 1 and here I0 should be basically cross, it can be anything. If this should be 0, then we have to get certain output which is 0, 1. Similarly for I2 should be equal to 1 and these inputs should be anything, it can be anything, cross, so cross, but I2 should be equal to 0, then we are going to get which is 1, 0. Similarly for I3 is equal to 1, so now it can be anything, cross marks, these are the cross marks, then we should get output as 1, 1. So if we solve this Karnaugh graph expression, we are going to get y0 is equal to I3 plus I2 over I1, and y1 is equal to I3 over I2. So now if you do this, so it is a priority encoder. Suppose at a time 2 and 3 is activated at a certain time, so 3 is having high priority, so its output is going to get displaced, its binary output is going to get displaced. So finally I can say that encoder is going to convert the any other number system to binary number system, and decoder is going to convert the binary number system to any other number system. So now we are going to discuss about the comparator. So comparator means basically we are going to compare the two inputs, or I can say two binary inputs. We are going to compare what is the nature of one and other. Let me take a 2-bit comparator. 2-bit means here bit A and bit B. Means A is one type of bit and B is one type of bit. So we can say simply A and B. Suppose what I am trying to tell you, suppose for this so this is basically 1-bit comparator. This is basically 1-bit comparator. 1-bit comparator means, see, for A and B, we are going to have only 1 bits. For A and B, we are going to get only 1 bits. So this is A having only 1 bit, and B is also having 1 bit. So we want to compare these two inputs. So by using this comparator, so we are going to get 3 outputs, either X, Y or Z. So Y is for equal. If both are equal, then only it is going to get activated. Y is nothing but, if A is greater than B, then A is going to get activated. That is nothing but A is less than B. So when A is less than B, that is going to get activated. So what is the expression for A is equal to B means, simply we are going to get A XNOR B. A XNOR B we are going to get here. A XNOR B. And whenever A greater than B means A B bar we are going to get. And whenever A less than B means you are going to get A bar B. So these are the expressions that you are going to get. So if you write the Karnaugh map for A and B, then we are going to get the certain expressions of output that we are going to get. So I have drawn this truth table for AB, both are having 1 bit. So 0, 0, 0, 1, 1, 0, 1, 1. So for this case, A is equal to B. So X is going to get activated and remaining things are 0. Similarly here A is less than B. So therefore D is going to get activated. Similarly here A is greater than B. So therefore Y is going to get activated and the remaining things are 0. Similarly here A is equal to B. So X is going to get activated and the remaining things are 0. So if you write the truth table for X, Y and Z in terms of AB, we are going to get, for X we are going to get X not B and Y is equal to A B bar and it is equal to A bar B. So same thing I have shown here. So therefore X we are going to get which is X not B, Y is nothing but A B bar and it is equal to A bar B. So basic operation of X is whenever A is equal to B, it is going to get activated. While basic operation is whenever A is greater than B, it is going to get activated. And for Z which is A less than B, means whenever A is less than B, then the Z is going to get activated. So far we can say these are the expressions that we are going to get, which is A X not B for X, for Y we are going to get A B bar, and for Z we are going to get A bar B. So this is the point that you always have to keep in your mind. For n bits, so for n bits, so suppose A is having n bits and B is having n bits, the number of combinations are, so total number of bits are n plus n 2n. So 2n bits, the number of combinations are to the power of 2n. So you can see clearly, suppose A is having n bits and B is having n bits, the total bits are 2n. So total number of combinations are to the power of 2n. So out of this, the number of conditions greater are, the number of conditions greater means here A is greater than B, the number of conditions are, which is to the power of 2n minus to the power of n by 2. And the number of combinations lesser are to the power of 2n minus to the power of n by 2. The number of conditions equal are to the power of n. So this is the point that you always have to keep in your mind. So listen carefully. For each having, suppose for these two inputs, each input having n variables. So total number of variables are, see basically what I am trying to say is, for these two inputs, each having a n bit. So therefore total number of inputs are, total number of input data is 2n. So total number of combinations are to the power of 2n. So to the power of 2n, to the power of n are number of equal conditions. So number of equal conditions are to the power of n. So out of this, the number of conditions greater than to the power of 2n minus to the power of n by 2, and the number of conditions greater than less, which is to the power of 2n minus to the power of n by 2. So this is the important form that you always have to keep in your mind. So for these two inputs, each input is having n bits. So total number of bits are 2n. So we are going to get the number of total combinations, the total number of combinations are to the power of 2n. Out of this, number of equal conditions are, the number of equal conditions are to the power of n, and the number of conditions greater is equal to the power of 2n minus to the power of n by 2, and the number of conditions lesser is equal to the power of 2n minus to the power of n by 2. So this is the point that you always have to keep in your mind. So whenever B is equal to B, we are going to get Ax not B. Whenever A is greater than B, we are going to get A B bar. Whenever A is less than B, we are going to get A bar B. So these are the expressions that we are going to get for X, Y and Z. So for n bit, these are two inputs, each having n bits. So total number of bits are 2n. So total number of combinations are to the power of 2n. So number of equal conditions are to the power of n, and number of conditions greater than, which is to the power of 2n minus to the power of n by 2, and number of conditions lesser are to the power of 2n minus to the power of n by 2. So this is the point that you always have to keep in your mind. See, for 2 bits, suppose you have 2 bits. So A is having 2 bits and B is having 2 bits. Then, see what is the expression of X? X is equal to A X naught B into A1 X naught B1 into A naught X naught of B0. Whenever this condition is satisfied, then only we are going to get the output as is equal to 1. So this is the expression for this one. A1 X naught B1 into A naught X naught A naught X naught B0. Similarly for Y. For Y, I wanted to know Y is activated only when A is greater than B. So here we are going to get which is A1 B1 bar plus A0 A1 X naught of B1 into A0 B0 dash. Similarly for Z, when A is less than B, that is going to get activated. So similarly we can say A1 bar into B1 plus A1 X naught of B1 into A naught bar into B naught. So this is the expression that we are going to get. So what I am trying to say is very simple. X is nothing but A1 x naught of B1 into A naught x naught of B1. For y, suppose y is nothing but when A is greater than B. So if A is greater than B means initially for if A1 is greater than B1, then we are going to get y is activated. So therefore A1 B1 bar plus, or suppose if A1 and B1 are equal, so A1 x naught of B1 dot, again A0 is greater than B0, so therefore we are going to get A0 B0 dash B0 bar. Similarly for Z, I already told you whenever A is less than B, Z is going to get activated. So if A1 is less than B1, then definitely Z is activated, so A1 bar B1 bar plus, suppose if A and B1 is equal means A1 bar A1 x naught of B1, again here A0 should be less than B dash B0, so therefore A naught bar B naught. So this is the expression that we are going to get. So this is the basis for the 2 bits. So x is equal to A1 x naught of B1 into A naught x naught of B naught. Similarly y is equal to, which is A1 B1 bar plus A1 x naught of B1 dot A naught B naught dash. Similarly that is equal to A1 bar B1 plus A1 x naught of B1 into A naught bar B naught. Suppose if you want to write for 3 bits, how you have to write is very simple. X is equal to A2 x naught of B2 into A1 x naught of B1 into A0 x naught of B0. Similarly, y is nothing but here A2, first integrate A2 B2 bar plus A2 x naught of B2, again here A1 B1 bar plus A2 x naught of B2 A1 x naught of B1, again A0 into B0 dash. Similarly, that is equal to A2 bar B2 plus A2 x naught of B2 into A1 bar B1 plus A2 x naught of B2 into A1 x naught of B1 into A0 bar B0. So these are the expressions for the 3 bits, for A adding with 3 bits and B is adding with 3 bits. So these are the expressions that we are always going to get. So finally what I am trying to say is very simple. Suppose for 2 bits means A is having 2 bits A1 A0 and B is having 2 bits B1 B0. If A is equal to B, then A1 should be equal to B1 and A0 should be equal to B0. So therefore we are going to get A1 x naught of B1 dot A0 x naught of B0. For y, when x is greater than, we can say A is greater than B, then only x is going to be activated. So we can have 2 conditions, which is A1 is greater than B1 or A1 is equal to B1 and A0 is greater than B0. So therefore simply we can say when A1 is greater than B1 is A1 B1 bar plus if A1 is equal to B1 is A1 x naught of B1 and A0 is greater than B0, so A0 B0 bar. Suppose that analogy to whenever A is less than B, that is going to get activated. So initially A1 is less than B1, so A1 bar B1 plus, suppose A1 B1 should be equal, so A1 x naught of B1 and then it should be this A1 should be less than B0, so therefore A1 bar B0. So these are the 2 conditions that we can get. Similarly for 3 bits, suppose A is having 3 bits and A2, A1, A0, B2, B1, B0. So A2 should be equal to B2, A1 should be equal to B1 and A0 should be equal to B0. So therefore simply we are going to get x is equal to A2 x naught B2, A1 x naught B1, A0 x naught B1. Similarly for y is nothing but A should be greater than B. A is greater than B at 3 conditions. The first condition is A2 is greater than B2. So we are going to get A2 B2 bar, or A2 is equal to B2 and then A1 should be greater than B1. So A2 x naught of B2 and A1 B1 bar. Similarly, here it should be, in third case you can get A2 equal to B2, A1 equal to B2, B1 and A1 is greater than B0. So you are going to get A2 x naught of B2, A1 x naught of B1 and A0 B0 bar. Similarly, that is nothing but here A should be less than B. Whenever A is less than B, we are going to get Z is equal to 1. So we can get in 3 cases, which is A is less than B2, then only we are going to get which is activated. So therefore A2 bar into B2, or if A2 is equal to B2 and A1 should be less than B1. So therefore A2 is equal to B2 and A1 dot B1 plus, and here third case you can get A2 is equal to B2, A1 is equal to B1 and A1 should be less than B0. So therefore A2 XOR of B2, A1 XOR of B1 and A0 dot B0. So these are the expressions that you always have to keep in your mind regarding this. X is allocated when A is equal to B and Y is allocated when A is greater than B and Z is allocated from when A is less than B. So these are the expressions that we are going to get for the corresponding comparator for 2 bits and 3 bits. Generally you can write for any number of inputs also, you can write like this consequently. Now we are going to learn about the another new concept is called as the gray code. See, gray code means in gray code representation of decimal numbers, two successive differs by only 1 bit. So basically here what I am trying to tell you here, in the gray code representation of the decimal numbers, two successive differs by only 1 bit. So therefore if you take the gray code from the corresponding binary bits, basically the two successive gray codes are going to differ by only 1 bit. So we can say very simply basically for the decimal numbers means we are going to convert decimal numbers into binary format, and for the binary format we are going to get the so for decimal numbers we are going to get the corresponding for the decimal numbers we are going to get the corresponding binary number, and for the corresponding binary number we are going to get the gray code, and the two successive gray codes are going to differ by only 1 bit. So we can say in gray code representation of decimal numbers, two successive differs by only 1 bit. So now we will see how to convert the binary to gray and gray to binary. So you can see this is the conversion from binary to gray. Suppose binary is having 4 bits, then definitely gray code is also having the 4 bits. So you can see clearly, so like this that we are going to get. So J3 is equal to B3 and J2 is equal to B2 XNOR of B3 XNOR of B2, and J1 is B2 XNOR of B1 and J0 is B1 XNOR of B0. So J3 is equal to B3, J2 is equal to B3 XNOR of B2 and J1 is B2 XNOR of B1 and J0 is equal to B1 XNOR of B0. So we are going to get like this, write this like in this format. This is MSB bit and this MSB bit, B3, B2, B1, B0. So you have to write in this manner. So like this you have to write this, and you have to write like this manner. So you have to write in this fashion, and then take as it is like this. So J3 is equal to B3 and J2 is equal to B3 XOR of B2 and J1 is equal to B2 XOR of B1 and J0 is equal to B1 XOR of B0. So this is the point that you always have to keep in your mind. So J3 is always equal to B3 and J2 is equal to B3 XOR of B2 and J1 is equal to B2 XOR of B1 and J0 is equal to B1 XOR of B0. So here B3, B2, B1, B0, so you write like this, you write like in this shape manner and take it as it is. So J3 is equal to B3, J2 is equal to B3 XOR of B2 and J1 is equal to B2 XOR of B1 and J0 is equal to B1 XOR of B0. So you are going to get like this. So this is the way that we are converting the binary format to gray code format. So this is the way that we are converting the binary format to the gray code format. So this is the way that we are converting the binary format to the gray code format. Suppose if you want to do the reverse process, if you want to go from gray to binary conversion, how to do this one? So simply you can see clearly, so this is a circuit which is going to show you how to do the conversion from gray to binary. So you can see clearly this is J3, J2, J1, J0. So from the circuit you can see B3 is equal to J3, B2 is equal to, so B2 is equal to nothing but which is J3 and the J3, so J3 and the, or you can say B3 and J2. So B3 XOR of J2 is nothing but B2. Similarly, B1 is nothing but is the B2 XOR of B2 XOR of J1. Similarly, B0 is the B1 XOR of J0. So listen carefully. B2 is nothing but which is the B3 XOR of J2 and B1 is B2 XOR of J1 and B0 is B1 XOR of J0. So listen carefully. B3 is equal to J3 and B2 is equal to B3 XOR of J2 and B1 is B2 XOR of G1 and B0 is B1 XOR of G0. So you can write in shortcut format. So G3, G2, G1, G0. So write as it is like this. So G3, take it B3. So B3 is equal to G3. Now do the XOR of these two things. Do the XOR of these two things. B3, G2, we are going to get B2. Again do the XOR of these two things. B3 and G1, we are going to get P1. Again do the XOR of these two things. We are going to get B1 XOR of G1 is nothing but B0. So this is the point that you always have to keep in your mind. So G3 is equal to B3 and B2 is the XOR of B3 G2 and B1 is the XOR of B2 G1 and B0 is the XOR of B1 G0. So this is the point that you always have to keep in your mind. So this is basically XOR. So this is the XOR. So this is the converted binary to gray and this is converted gray to binary. So this is the important point that you always have to keep in your mind. So now we discuss about the BCD. BCD is nothing but binary coded decimal. So here basically suppose from 0 to 9 we are going to represent. So from 0 to 9 we are going to represent the binary digits with the corresponding 4 bits. See for 0 to 9 for 0 to 9 decimal numbers we are going to represent the corresponding binary bits by 4 binary bits. So now suppose if it is more than 9 like 10. Then for 1 we have to represent the 4-bit binary and for 0 we have to represent the 4-bit binary. This is in terms of BCD. So BCD means binary coded decimal. For each decimal number we have to represent with respect to 4 binary digits. So for 9 is 1 or we can say suppose for 2 is there. 2 means you have to represent in the 2 fashion which is 1 is 0001 and 2 is 0010. So like this we have to represent. So for each and every binary, for each and every decimal digit we have to represent with respect to 4 binary digits. So this is called as a BCD, binary coded decimal. See a small example. Suppose BC for this decimal number 9 we are going to represent by 4-bit binary 1001. For this 13 decimal number we have to represent for 1 we have to represent by 4-bit and for 3 also we have to represent by 4-bit. So for 1 0001 and for 3 which is 0011. So for 1 we are represented by 4-bit binary, for 3 also we are represented by 4-bit binary. So this is called as a BCD representation. So for each decimal digit it is represented with the 4-bit binary. So each decimal digit if you are going to represent by 4-bit binary it is called as a BCD. So each decimal digit if it is represented with 4-bit binary it is called as a BCD representation. So now we are going to discuss about the 4-bit BCD adder. So how to do the 4-bit BCD addition means suppose we have two A and B as inputs. A is having a 4-bit and B is having a 4-bit. Then how to do the summation of these things? So basically what the things that we can get. See I already told you. See suppose if you have two 4-bit numbers. So minimum number is 0 and here also minimum number is 0. Here maximum number is basically the help of 4 bits, the maximum number that we are going to get is so we are going to get 15. Here also we are going to get 15. So therefore now the natural number is here is 15 and here also natural number is 15. So now I am going to do the 4-bit BCD added. So 4-bit BCD added I am going to do here. So this is the 4-bit BCD added. So you can see clearly. So this is A bit and this is a B bit. So B0, B1, B2, B3, A0, A1, A2, A3. So now what I am going to do basically, I am going to keep here 4-bit parallel ladder. So I am going to keep the 4-bit parallel ladder. So output we are going to get S0, S1, S2, S3 and C4. So S0, S1, S2, S3, C4 we are going to get here. So now here from this C4 we have to take here and we have to go to some exact, we can say OR gate we have to keep, and this is the I. I is nothing but S3, S2 plus S3, S1. So I is equal to S3, S2 plus S3, S1. So if this is activated, then if suppose this OR gate is activated, then what is going to happen? If any of this input is 1, then definitely it is going to get activated. So when this is activated, you are going to get here 1, 1, 0, 0. So 0, 1, 1, 0 means we are adding the 6 here. So 0, 1, 0 is nothing but 6. So if it is 0 means, suppose if it is not activated means 0. So here always you are going to get 0 here. So here also you are going to get 0. Suppose if this is activated means you are going to get output as 1 here. So you are going to get 0, 1, 0 and here also you are going to get carry as 1 here. Suppose if it is not activated means 0. So you are going to get 0, 0, 0, 0 and here you are going to get 0 here. Then you have to add extra 6. If this is activated, you have to add extra 6 to this output. Then you are going to get the actual output in the terms of the BCD. So in the terms of BCD that you are going to get. So this is again 4-bit parallel ladder. So then you are going to get the actual output. So this is for the range it can cover. The range it can cover. So this is for 1 bit and this is for the other bit. So this is the binary bit for 1 bit and this is for the binary bit for other bit. So the range it can cover is 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. See, what I am trying to say is only it can have a range from only 0, 0 to 19. So this can read only data from the summation result. It can only read from 0, 0 to 19 only it can read. Suppose if you add 4 plus 3, 7, yes, 7 is there, so it can be represented here. And if you add 9 plus 9, 18, 18 also we are going to get in this format, which is, it is going to represent like this. Here it is 1 and here it is 8. 8 means here, basically we are going to get 1, 0, 0, 0. Similarly, suppose 7 plus 7, 14 plus is there in this one, so it is in this range, so it can represent 1, 4 is nothing but, here it will be 1, here it will be 4, 4 is nothing but 0, 0, 1, 0. So like this it is going to represent. So this is for this higher number and this is 4 is for this lower 4 bits number. So each bit we are going to, each decimal number we are going to represent by 4 bit. So this is the 4 bit for the lower one and this is for the upper one. Only this can read, only this is the range it can read from 0, 0 to 19. Only this is the range it can read only from 0, 0 to 19. Suppose if you go for 9, see, we can say 9 plus 9 because basically means only 0 to 9 we are going to add. So 0 to 9 and 0 to 9. 9 plus 9 is 18. Yes, it can read 9 plus 9, 18 also it can read. So this is a point that you always have to keep in your mind. Only it can read up to 0, 0 to 1 only it can read. So finally I can say, suppose 0, 3 means it is going to represent in this fashion 0 and here 0, 0, 1, 1. Suppose if it is 19 means it is going to represent like this. This is 1 and this is 9. 9 means 1, 0, 0, 1. So only this is the data it can represent. So whenever this is activated, it will become 0, 1, 1, 0 and it also is going to become output 1. Suppose it is not activated means you are going to get 0, 0, 0, 0 and not 0 means we are going to add 0 to this output, same output that we are going to get. If you add 0 to this output, same output that we are going to get. So this is the important point that you always have to keep in your mind. So this is basically doing the 4-bit BCD adder. So 4-bit BCD adder. So it can get the output range from 0, 0 to 19. So this is the circuit diagram that you always have to keep in your mind. So now we are going to discuss about the latches. So after that we are learning about the, we can say, combination circuits. So after that we are learning about the combination circuits. It means that present output is depending only on the present input. So whenever the present output depends on the present input, then we are going to call that system as the convolutional circuit. So this is a very important point that you always have to keep in mind. So whenever the present output is dependent, whenever the present output is dependent only on the, so whenever the present output is dependent on the present input, then we can call the system as the convolutional circuit. Otherwise, if the present output is depending upon the present input as well as on the past output, then we are going to call that system as the sequential circuit. So up to now we have learned about the convolutional circuits, but now we are going to learn about the sequential circuits. So let me give you the definitions of these two things. So the first thing is that we always have to keep in mind, in convolutional circuits, the present output is depending only on the present input. Then that system is said to be a convolutional circuit. Otherwise, whenever the present output is depending on the present input as well as the past output, then we are going to call that system as the sequential circuit. So before learning about sequential circuits, first we have to learn or we have to understand the basics of the latches. So you can see clearly these are called as the latches. So I have taken a NAND gate. And I have given, you can see feedback. So you can see this is a NAND gate. Here I am going to call this as the S, and here I have taken the feedback from this one. And similarly this is the output. So I have given for this input is R, and the other input I have taken from here from this feedback. So in the convolutional circuits there will be no feedback, but in the sequential circuits there will be always feedback. In the convolutional circuits there will be no feedbacks, but in the sequential circuits the feedbacks are going to get present. So this is called as the, let me assume this as an input S and this is the R input, and let me assume this as a Q and this is a Q bar. It is a just a notation that I am going to assume. This is S, this is R, and this is Q, and this is the Q bar. I am going to assume like this. Suppose I am going to draw some truth table. You can see S, R, Q, Q bar. See, these are the two inputs. So for two inputs, we are going to get 4 combinations, because for n variables, we are going to get 2 to the power of n combinations. So therefore 0, 0, 0, 1, 1, 0, 1, 1. See, whenever you give 0, 0, I already told you for a NAND gate, if one of the input is 0, definitely no matter whatever the other input, always we are going to get output as 1. This is a very important point, listen carefully. For a NAND gate, if one of the input is 0, no matter whatever the other input, definitely the output is always equal to 1. So if S is equal to 0, definitely Q is equal to 1. If R is equal to 0, no matter whatever other input, always you are going to get this also equal to 1. So Q is equal to 1 and Q bar is also equal to 1. So this is called as the invalid, because always we want Q and Q bar to be complement of each other, but they are same here. So this is the reason we are not considering this input. So we are not considering this input. It is called as the invalid state, or you can say invalid state. So basically we want Q and Q bar to be complement of each other, but here we got the same results. So we are not going to consider this. We are not going to take this one. So this is called as the invalid state. Suppose if S is equal to 0 and R is equal to 1, what is going to happen? As I already told you, whenever S is equal to 0, irrespective of the other input, definitely the output will be equal to 1. So if this is 1 and this is also 1, so 1 is again 1, IM complement is nothing but 0. So you are going to get Q as 1 and Q bar as 0. So Q is equal to 1 and Q bar is equal to 0, you are going to get. Similarly here, suppose if I give input 1 and 0, if I give one input 1 and 0, you can see clearly, if I give here 1 and 0, I have already told you, now for this R is equal to 0, no matter what was the input, definitely you are going to get this as 1, means Q bar is equal to 1. So this is taken as a feedback. So S is equal to 1 and here also 1. So 1 into 1, 1, again 1 complement is equal to 0. So Q is equal to 0, Q bar is equal to 1. Yes, Q is equal to 0, Q bar is equal to 1. Then, so you can say these two states are complement of each other. Here Q is equal to 1 and Q bar is equal to 0, and Q is equal to 0, Q bar is equal to 1. Yes, both are having the complement of each other. So these are the valid states. And if you give 1 1, if you give 1 1, if you give 1 1, whatever the previous state, same is it is going to present here. Suppose if the previous state is 0 1, now also it is going to present 0 1. If the previous state is 1 0, now also it is going to present 1 0. So it is called as a memory. So therefore, if you give 1 1, if you give 1 1, whatever the previous output, same thing is going to present now also. So it is called as a memory. So it is going to act like a memory. So this is an important point that you always have to keep in your mind. So whenever you give 1 1, so no matter, so if the input is the output 0 1, same thing we are going to get now also. If the output is 1 0, after giving again, we are going to get same output. So it is going to act like a memory. So this is a point that you always have to keep in your mind. So finally I can say that for this NAND, this is basically we have made the latch with the help of NAND gates. So therefore for SR, Q, Q bar, when 0 0, you are going to get 1 1. It is called as an invalid state because both are having the same nature. And 0 1 means you are going to get 1 0. For 1 0 means you are going to get 0 1. And for 1 1 means you are going to get memory. I will explain all these things with the help of this concept. Suppose we can make the latch with the help of NOR gate also. So I am going to take this NOR gate. So you can see same thing, just I replace NAND gate by NOR gate. I am going to get like this. You can see clearly same circuit, just I replace the NAND gate by NOR gate. These are. But now I have interchanged these positions. So I have interchanged these positions, which is Q bar and Q. So this is Q bar and this is Q. I am going to take this like this. So now we'll see what is going to happen. So this is yes, this is R. So two input variables. So now we'll see what is the combination. Two input variables means 4 combinations 0 0 0 1 1 0 1 1. See here I already told you. See if you do 0 0, if you do 0 0, no matter, see if you do 0 0, whatever the past output, same thing that you are going to get also. So it is going to act like a memory. So we can say whenever you do 0 0, whatever the previous output, same output also you are going to present. So it is going to act like a memory. Suppose if I give 0 1, suppose if I give 0 and 1, I already told you for NOR gate, if one of the input is 1, definitely whatever the other input, always it is going to become 0. So therefore, if from NOR gate, if one of the input is 1, irrespective of the other input, always the output is equal to 0. Here S is equal to 0 and R is equal to 1. So this is 1, no matter whatever the other input, always we are going to get here 0. If this 0, it is also going here. So 0 0 is 0 and then bar is nothing but 1. So Q bar is equal to 1 and Q bar is equal to 1 and Q is equal to 0. So we are going to get 0 1. This is 0, this is 1. So suppose if I give 1 0, this is 1 and this is 0. I already told you if one of the input is 1 or NOR gate irrespective of the other input, definitely the output is equal to 0. So therefore this is 1 0 right. So this will be always equal to Q bar is equal to 1. See S is equal to 1, no matter whatever the other input, definitely the output is equal to 0, so Q bar is equal to 0. So I have taken here now 0 and 0, 0 plus 0, 0, 0 bar, 1 bar is nothing but 1, so Q is equal to 1, yes Q is equal to 1 and this is 0. Suppose if I give same inputs, then what is going to happen? 1 and 1, I already told you for NOR gate, if one of the input is 1, irrespective of the other input, definitely the output is nothing but 0. So this is also 0 and this is also 0. So both are 0. So both are in the same states. So it is called as the invalid state. Because we want the states to be congruent of each other, but we got the same states. So it is called as the invalid state. So this is the point that you always have to keep in your mind. See, let me tell you some important points regarding the invalid state. See here, 1, 1 is an invalid state, here 0, 0 is an invalid state. So listen carefully, I will tell you why it is called as an invalid state. See, the condition is both are having 0, 0, yes, but after giving this input, if you give S is equal to 1, R is equal to 1, you got 0, 0. After this, if you give the memory, if you give 0, 0, then these values can be either 0 1 or 1 0. They will be not like a memory state. So listen carefully. Suppose I give input as 1 1. then the output is 0 0. Suppose if I give a 0 0, it should be actually memory 0 0, but it is going to act like a 0 1 or 1 0 based on the preference of which device is acting very fast. So listen carefully. Suppose if I given 1 1, now the output is 0 0. After this I am giving 0 0. So ideally I should get the same value as 0 0, but it will never be like that because it may be 0 1 or 1 0 because of the whichever device is acting very faster. Based on that, the output is going to get very either 0 1 or 1 0. So this is the important point. So we don't know exactly what is the output after giving this input. After this input, if you give any other input, we don't know what is the exact nature of the output. So because of that reason only, we are going to call this as the invalid state, because after this input, if you give memory input, we don't know what is the output, either it can be 0 1 or 1 0. So because of this reason, because they are going to change because of the whichever device is acting very fast, so it is going to fluctuate. So because of this reason only, we are going to call this as the invalid state. Same thing for here also. So if you give 0 0, we are going to get 1 1. After this, if I give 1 1, the output can be either 0 1 or 1 0 based on whichever device is acting very fast, because no matter whichever the device you take, no matter whatever the similar properties of device you take, there will be negative values are purely identical. Small amount of variation can be present. In many of these, they are the similar materials. Because of this, whichever device is going to act very faster, one is going to get changed 0 to 1 or 1 to 0. So finally I can say that, see, after the invalid state, if you give for memory, if you give the memory input, the output will be never the past output. It will be always 0 1 or 1 0 based on the whichever the device is acting very fast. So because of this reason only we can say that we are not using this state. So this is called as the invalid state. So out of these 4 states we are using only first 3 states, but not the 4th state. So this is the important point that you have to always keep in your mind. So this is the latch with the help of NAND gate, and this is the latch with the help of NOR gate. So now if you see clearly an important point here, suppose I have given 0 1, it came 1 0. Suppose if I given 1 0, again the output is changed to 0 1, but I don't want to change like this. Even if the input is varied, suddenly due to some mistakes, if the input is varied, I don't want the output to vary. Then we have to do the circuit. So this is the circuit. It is going to help you. Suppose due to some sudden changes in the input, the output I don't want to change. Then you have to use the circuit. So this is circuit which is going to help you. Even if the sudden change in the input, the output will never change. Whenever you make the clock is equal to 0. So now we'll discuss something more about this one. So now this is the first circuit that we have studied. So for this circuit, I am going to extend this 2 lines and I am going to 1 more NAND gates. This is a NAND gate, here is NAND gate. So this is the first circuit that we involve with the help of NAND gates. So I already told you this is Q, this is Q bar, this is XNR, no? So we are going to extend this one and give it to 2 NAND gates. So this common point, this common input I am going to give to clock signal, and this is called as the S and this is called as the R. So now we will see what is actually going to happen. See, suppose clock is equal to 0. Suppose I make clock is equal to 0. Then what is going to happen if clock is equal to 0? In respect of the other input, I already told you, for NAND gate, if one of the input is 0, no matter whatever the other input, always the output is nothing but 1. So you are going to get 1 and 1. If this is 1 is 1, I already told you, whenever you go for 1 1, if it's more than 1, we are going to get memory state. So 1 1 is, if these two are 1 1 is, we are going to get a memory state. So therefore, when clock is equal to 0, irrespective of the other inputs, I already told you, we are always going to get a memory state. Suppose if I make the clock is equal to 1, if I make clock is equal to 1, then what is going to happen? If clock is equal to 1, I can do some combinations. So 2 input means 4 variations, 0 0, 0 1, 1 0, 1 1. See, if S is equal to 0 and R is equal to 0, what is going to happen? If this is 0, this is 1. 0 into 1 is 0, 0 bar is equal to 1, so this is 1. Here also 0 into 1 is 0, 0 bar is also 1. So both are 1, Neither one is again is a memory state. Just now we have learned is a memory state. So this is the again memory state. Suppose if you give 0 1. So 0 1 is nothing but this is I already told you this 0 into 1 is 0. 0 1 is equal to 1. So this is 1 we are going to get. And here what you are going to get, it is nothing but 1 into 1 is 1. 1 comma 1 is equal to 0. So here we are going to get 1. Here we are going to get 0. So whenever x is equal to 1 and r is equal to 0, we got 0 1. So therefore you are going to get now 0 1. You can see clearly 0 1. Similarly, if input x is equal to 1 and r is equal to 0, then 1 into 1 is 1, 1 complement is equal to 0, here you are going to get 0. Again, 1 into 0 is 0, 0 complement is equal to 1. So therefore, here you are going to get basically, so 1 0 means you are going to get 0 1. So this is 0, this is 1. So you are going to get 1 0. Same thing from the graphic graph. You can say this is 1 0 you are going to get. Suppose if I give 1 1, then what is going to happen? If I give 1 1, definitely 1 to 1 is 1, 1 complement is equal to 0. Here also 1 to 1 is 1, 1 complement is equal to 0. So again 0, here also 0. So whenever 0 0, I already told you it is the invalid state. So invalid state is nothing but if it is a NAND gate. If it is a NAND gate, so you are going to get 1 1. If it is a NAND gate, I already told you the invalid states are 1 because they are same thing here. So this is called as the invalid state. So this is the thing that we are going to get. So this is the point that you always have to keep in your mind. So this is called as the SR flip-flop, SR flip-flop or SR latch. So SR flip-flop, you can see when the clock is equal to 0, irrespective of the input variables, if any input variables are changing, output is always memory. So this is the advantage of this circuit. So this is the point that I am trying to tell you. So this is the very important point that you always have to remember the concepts. And what I told you, invalid means basically after this input, if you do the memory, definitely this output will be, everything will be same only. It will be 0 1 or 1 0. Based on the device, which the device is acting very fast. So we can't predict the output. And so therefore, because of this reason, we are not using this state. So it is called as the invalid state. So in the same manner, we are going to do same thing for the second latch also. For second latch, we have used the NOR gate. So NOR gate, here also NOR gate, here also NOR gate we have seen. So I already told you this is the Q bar, this is the Q. So therefore, now we are going to extend this line and we are going to keep the AND gate, not NAND gate. Here we are going to use the AND gate. So then, this is the clock, this is this, this is AND. So now we will see what is going to happen for this circuit. Same thing here also. So clock, SR, Q bar. So whenever the clock is equal to 0, irrespective of the other inputs, always you are going to get here 0 and 0. So therefore, whenever 0 0, I already told you what is that? It is the memory state for the NOR gates. So this is a memory state. It is a memory state. Just now I have already told you. Suppose if I give clock as 1 and if I change this inputs, then what is going to happen? For 0 0. For 0 0 means again these are 0 0. Again this is memory state. Just now we have seen. Again, if clock is equal to 1, then this is 0 1. 0 1 means again we are going to get same thing 0 1. So 0 1 means just now we have seen for this it will be 0 1. So this is 0 and this is 1. So we are going to get 0 1. Similarly for 1 0, for 1 0 means here 1 here 0. So we are going to get here 1 and 0. So we are going to get 1 0. Similarly if you give 1 1, if you give 1 1, here also 1 1. So if you give 1 1, I already told you, you are going to get 0 0 for this last circuit. So 0 0 we are going to get. I already told you whenever you get 0 0, it is called as the invalid state. So it is called the invalid state because after this state, if you give memory input, the output will be never the memory. It will be not the first output, but it will be either 0 1 or 1 0 based on whichever the device is acting very fast. So we can't tell what is the output, exact output. So because of this reason only, we are going to call this as the invalid state. So this is the point that you always have to keep in your mind. So now we will discuss about the SR flip-flop. So basically SR flip-flop, we can make the flip-flop based on NAND gates or NOR gates. We can use any one. So generally I am going to give a general block diagram. So this is SR flip-flop. This is a clock signal. So we can say SR and this is a clock signal. SR and this is the clock. This is the Q and Q bar. So now I am going to draw the general circuit diagram. So this is the SR and the clock signal. This is the Q and Q bar. So now I am going to draw the general, you can say general truth table. So clock here is SR, Q, Q bar. I already told you whenever the clock is 0, irrespective of the other inputs, always you are going to get a memory state. Always you are going to get a memory state. Same for both NAND gates and also for NOR gates. Just now we have seen the circuit and the EXO circuit. Same thing that we are going to get. Suppose if clock is equal to 1, then if S is equal to 0 and R is equal to 0, then we are going to get memory state. Same for both the things. The circuit and previous circuit, both the things are same. So this is also memory. So the clock is equal to 1 and this is 0, this is 1. So also you are going to get 0 1. Same thing for this one and also 2 this one. Suppose the clock is equal to 1 and S is equal to 1, R is equal to 0, you are going to get same thing which is 1 0 for this circuit and also for the previous circuit. Suppose the clock is equal to 1 and S is equal to 1 and R is equal to 1, you are going to get inverted state, means Q is equal to Q bar. Suppose if you are going to use only NAND gates, then you are going to get this as 1 1. If you are going to use the NOR gates, then you are going to get 0 0. But the same concept, just Q is equal to Q bar. So therefore simply we can say that in order to memory state means after this input, if you give the memory input, always the memory will be not equal to this output. It will be 0 1 or 1 0 based on which of the base is acting very fast. So because of this reason only, we have an accurate result. So therefore because of this reason we are going to call this as the invalid state. So this is a very important truth table that you always have to keep in your mind. So this is a clock SR Q Q bar. So 0, this is no matter what are the input is always going to get the memory. So for 0 0 memory, for 0 1 0 1, for 1 0 for 1 0, for 1 1 it is a invalid state. Invalid state means Q is equal to Q bar. So this is a very important truth table that you always have to keep in your mind. So whenever the clock is equal to 0, in respect to of the S and R, always you are going to get the memory. So whenever the clock is equal to 1 and S is equal to 0, R is equal to 0, always you are going to get the memory. So therefore, in this all these things, clock is equal to 1. So for 0 1, we are going to get 0 1. For 1 0, you are going to get 1 0. For 1 1, you are going to get invalid state. Invalid state means Q is equal to Q bar. And what I told you, for invalid state means Q is equal to Q bar. So invalid state means Q is equal to Q bar. And what I told you, because after this, if you give any memory, definitely you are not going to get this invalid state as a memory. It will be always either 0 1 or 1 0 based on the which of the base is acting very fast in the circuit diagram. So because we can't predict the output. So because of this reason we are going to call this as the invalid state. So this is a point that you always have to keep in your mind. So now listen carefully. Now I am going to draw the excitation table. So this is a very important thing. The excitation table that you always have to understand. So excitation table is nothing but. So this is the present. This is called the past output, and this is the present input. These are also present inputs. So simply we can say this is the. We can also call this is basically past. We can say this is the present input, and this is the future output. So these are the inputs that are going to change the present output to future output. So listen carefully. So these are the inputs. If you give these inputs, the output is going to change from this to this. So if you give these inputs, the output is going to change from this to this. So what is that input that we have to give? So therefore, output is going to change from Q1 to Q1 plus 1. That is the agenda of this table. So this is called as the excitation table. So these are the two things. So 0 to 0, 0 1, 1 0, 1 1. So these are two inputs. So two things means four combinations. 0 0, 0 1, 1 0, 1 1. See, if I want to change 0 to 0, then what I have to do? See, if I want to change from 0 to 0, whether I can give memory 0 0, or whether I can give 0, 1. See, if I give 0, 0, I am going to get same thing as memory 0, 0. Suppose I want to change from 0 to 0. Then what is the input that I have to give? See, S is equal to 0 and R is equal to 0. Then I am going to get 0, 0 means it is a memory. So previous thing is going to get present here. Suppose if I give 0, 1, then also you are going to get this as the same. So therefore we can say this is always, S is always equal to 0, but R can be the 0 or 1. So therefore we can say, finally we can say 0, comma x. So same thing I have written here. So 0, comma x. You can see 0, comma x. Suppose if I want to change from 0 to 1. Suppose if I want to change from 0 to 1, then what I should do? It is simple. If you want to change from 0 to 1, what is the value of S? See, here S can be either, it can be 1, 0, it can be 1, 0. Only 1, 0 is going to get do this process. Only 1, 0 is going to do this process. If we give 1, 0, then QM is going to change to 0 to 1. So this is the input that we have to give here. Similarly, you can see clearly 0 to 1 means you have to give 1, 0. Similarly, if I want to change from 1 to 0, then what I have to do? Suppose if you want to change from 1 to 0, then I already told you, you have to give S is equal to basically 1 and 0. Sorry, this is S is equal to 0 and R is equal to 1. Because if we do S is equal to 0 and R is equal to 1, then 1 is going to change to 0. So this is the thing that you always have to keep in your mind. Suppose if you want to change from 1 to 1. So 1 to 1 is memory. So memory means 0, 0. And also you can give 1, 0. So 0, 0 or 1, 0. So definitely x comma 0. So this is x comma 0. So these are the inputs that you have to give. So therefore the output is changing from Qn to Qn plus 1. So if you do these inputs, the output is changing from Qn to Qn plus 1. So if you want to change from 0 to 0, you can give either 0, 0 or 0, 1. So definitely this is 0 cross x. If you want to change from 0 to 1, always you have to do 1, 0. If you want to change from 1 to 0, definitely you have to do 0 to 1. If you want to change from 1 to 1, then you can do 0, 0 or 1, 0. So therefore cross comma 1, cross comma 0. So cross comma 0. So this is the excitation table that you always have to keep in your mind. So whenever the output is changing from 0 to 0, you can be either 0, 0 or 0, 1 means 0 cross. If you want to change the output from 0 to 1, you have to give either 1 comma 0 always. If you want to change the output from 1 to 0, always you have to give 0 comma 1. Similarly, if you want to change the output from 1 to 1, then you can give 0, 0 or you can give basically 1 comma 0. It means x comma 0. So this is the input that we can give here to get this one. So this is called as the excitation table. So now what I am trying to tell you is basically if you take S, R, Qn, if you take S, R, Qn, so with these three combinations means you are going to get 8. With 3 inputs you are going to get 8 combinations. So for that, if you figure out the Q of n plus 1, so if you figure out the Q of n plus 1, for that input, the Qn is changing to Qn plus 1. So if you got a truth table and if you do the Karnaugh Map simplification, you are going to get Q of n plus 1 is equal to R bar into Qn plus S. So this is the expression that we are going to get. It is called the characteristic equation. So listen carefully. See for S, R and Qn. If you take these 3 inputs and give for 3 inputs means for 8 combinations. For these 8 combinations, if you figure out the Q of n plus 1, so for this S and R, if you give input, the Qn is changing to Q of n plus 1. Then if you draw the truth table and if you find the Q of n plus 1 and then if you write the Karnaugh map, then you are going to simplify it and you are going to get the expression Q of n plus 1 is equal to R bar into Qn plus S. So this is called as the characteristic equation and this is called as the excitation table. So now I am going to draw something which is called as a state diagram. So now I am going to draw a state diagram. You can see clearly, suppose if I want to change the output from 0 to 0. So if I want to change the output from 0 to 0, again means I have to give S is equal to 0 and R is equal to x. So S is equal to 0 and R to x. Suppose if I want to change the output to 0 to 1, then I have to give If output want to change from 0 to 1, I have to give S is equal to 1 and R is equal to 0. You can see clearly from here. Suppose if I want the output to change from 1 to 0, so to 1 to 0 means I have to give S is equal to 0 and R is equal to 1. S is equal to 0 and R is equal to 1. Suppose if I want the output to change to 1 to 1 only, then I have to give S is equal to X and R is equal to 0. So S is equal to X and R is equal to 0. This is basically diagram of this one. So this is basically diagram, pictorial diagram of this table. So this is called as the state diagram and this table is called as the excitation table. So we can say that this table is basically showing the pictorial graph of this table. So this graph is going to show the pictorial representation of this table. So this is the excitation table and this is called as the state diagram. So this is an important thing that you always have to keep in your mind. So if you want to change the output from 0 to 0, you can do either 0 1. If you do 0 1, it is going to become 0 to 0 or 0 1 also you can give. Similarly 0 to 1 means you can do, you have to give 1 0 and 1 to 0 means you have to do 0 1 and 1 to 1 means it is a x comma 0. So this table that you always have to keep in your mind. Now we are going to learn about the JK flip-flop. So JK flip-flop is basically, I already told you this is a circuit. So this is a, so basically I already told you this is a circuit. This issue of this, so very important thing that I already told you in the previous circuit. So this is the circuit that we have already seen. This is R, this is the clock, and this is the input, these are the NAND gates. So we are going to these two NAND gates. So there is a feedback like this and this is the Q and Q bar. We have seen, this is called as the XR flip-flop, but we have to do something extra, which is we have to take the feedback from this to this input and this to this input. So if you take the feedback from this output to this input and from this output to this input, so whatever the resultant flip-flop that we are going to give is called as the JK flip-flop. Similarly, now in the market I already told you, so this circuit I already told you SR, these are AND gates, this is the clock, and these are two NOR gates. So this is called the Q bar and this is Q. So I already told this point. So now you take the feedback from this point to this point and from here to here. So this is called as the J and this is called as the K. So basically what is the main agenda of this one is, now whatever the invalid state we are going to use it. See whatever the invalid state now we are going to use it for toggling purpose means it is going to, means we can even use the invalid state also, but it is going to vary continuously. So we can say the basic agenda of using the JK flip-flop is to use, it is basically to use the invalid state also. Invalid state also we are going to use, but whatever the output that we are going to get, it is that basically it is in the toggling mode. Toggling means continuous change, continuous fluctuation from 1 to 0, 0 to 1, a continuous fluctuation is going to happen and the remaining states are same as the SR flip-flop. Only thing is the 1, the invalid state is going to get changed and remaining everything is same as the SR flip-flop. So these two circuits are equal, so we are going to write like this. So the general block diagram, JK flip-flop, this is the clock and this is the Q and Q bar. So this is the clock, JK, Q bar. I already told you, whenever the clock is equal to 0, irrespective of the other inputs, always we are going to get memory. So whenever the clock is equal to 1, in all these cases, for 0 0 we are going to get memory, for 0 1 we are going to get 0 1, for 1 0 we are going to get 1 0, for 1 1, in the previous case SR flip-flop, there we are going to get the invalid states, but now this is called as a toggling mode. Toggling means continuous variation of 0 to 1 and 1 to 0 in a very speed manner, which is going to fluctuate like a very super fast express, 0 to 1 and 1 to 0 continuously. So it is not in our control. So this is called as the toggle or raise around condition. So if you keep the feedback like this continuous, it is going to get changed like a super fast express from 1 to 0 and 0 to 1. So the remaining things are same as the SR flip-flop only. But the only thing is this is going to change to toggle means it is called as the raise around condition. So now I will draw the basically I will draw the excitation table and also the state diagram. So now I want to change, so listen carefully, I want to change the basically the output from QN to QN plus 1. So with the help of this input, so if I give this input, the output is changing from Qn to Qn plus 1. So what are these inputs that we need to fill out? So listen carefully, very important point. See, suppose if you want to change the output from 0 to 0, either you can give memory 0 0 memory, or you can give 0 1. So therefore simply we can say 0 cross, because J is always equal to 0, but K can be 0 or 1. So because of this reason it is 0 cross. Suppose if you want to change the output from 0 to 1, definitely you can give either 1 comma 0 or 1 comma 1. So 1 comma 0 or 1 comma 1 we can give. So because of this reason J is always equal to 1, or K can be 0 or 1. So because of this reason it is 1 cross X. Whereas if you want to change the output from 1 to 0, then definitely you can give either as 0 1 or either you can give 1 1. So J can be 0 or 1, but K is always equal to 1, which is cross comma 1. So similarly, if I want to change the output from 1 comma 1, then I can give 0 comma 0 as a memory, or I can give 1 comma 0. So J can be either 0 or 1, but K is always equal to 0. So this is S comma 0. So this is called as the excitation table. So problem is it is going to change from 0 to 1 and 1 to 0. So this is basically an excitation table. So 0 0 means you have to give input as 0 1, 0 cross. If you want to change output from 0 to 1, you have to give 1 comma X cross as input. And if you change the output from 1 to 0, you have to give input as cross comma 1. And if you want to change the output 1 to 1, you have to give input as cross comma 0. So this is called as the excitation table. So now basically if I want to represent in the pictorial graph, so we are going to represent in this pictorial graph. Suppose if the output is 0, I want that again same output 0, then we have to give J is equal to 0 and K is equal to X. So by this input we are going to get the same output. Suppose if I want to change the output from 0 to 1, then I have to give input of J is equal to 1, K is equal to X. So if I want to change the output from 0 to 1, I have to give J is equal to 0, J is equal to 1 and K is equal to X. Suppose if I want to change the output from 1 to 0, I have to give J is equal to X and K is equal to 1. So you can see if I want to change the output from 1 to 0, I have to give J is equal to X and K is equal to 1. Similarly, if I want to change the output from 1 to 1, if I want to change the output from 1 to 1, I have to give J is equal to X and K is equal to 0. So you can see clearly. So whatever this table, I have made it in the terms of pictorial graph. So this is called as the state diagram and this is called as the excitation table. So now we are going to get the characteristic equation. I already told you, if you take J, K and Qn, for J, K, Qn, for 3 inputs you are going to get 8 combinations, and for JK input, then Qn is changed into Qf and DS1. So if you fill out like that, for JK input, for a certain JK input, the Qn is changed into Qf and DS1. So now for Qf and DS1 you write in terms of JK and Qn, the input came out. If you solve this one, if you simplify this one, finally we are going to get Qf and DS1 is equal to J into Qn bar plus K bar into Qn. So this is the characteristic equation that we are going to get. So this is all about this one. See, JK flip-flop, all these things are same except this invalid state. In the previous state is the invalid state, but now we are going to get a toggle means ratio means complete. We can say like super fast expression is changing from 0 to 1 and 1 to 0. So this is a point that you always need to remember because of the feedback is present. In XR flip-flop there is no feedback from output to input, but now there is a feedback in the JK flip-flop. Now we are going to learn about the B flip-flop. See, B flip-flop, we are going to make the B flip-flop from the JK flip-flop itself. So from JK flip-flop, we are going to make the B flip-flop. So listen carefully. This is JK flip-flop. JK, clock signal, Q, Q bar. So these are the two outputs. So if you keep a NOT gate, between the J and K, if you keep a NOT gate between the J and K, and this is called as a common input, this is called as the D. So this is called a data input. Then we can say that this is called as a basically D flip-flop. So if you keep a NOT gate between the J and K, and this column input is called as the D, it is called as the data input, or we can say this is called as the D flip-flop. So it is equivalent to a D flip-flop with a D input, clock signal, Q and Q bar. So now if you see clearly, there is only one input with the clock, so clock and D. So Q and Q bar. See, when clock is equal to 0, when clock is equal to 0, irrespective of the value of X, means we are going to use this state. Irrespective of the value of this X and X, always use memory state. Suppose if clock is equal to 1 and d is equal to 1, d is equal to 1 means j is equal to 1 and k is equal to 0. So whenever j is equal to 1 and k is equal to 0 means it is equal to 1 comma 0. So this is 1 comma 0. Similarly, if clock is equal to 1 and d is equal to 0, if d is equal to 0 means this is 0 and 1. So 0 and 1 means again it is 0 and 1. So 0 and 1. So therefore this is basically evaluating 0 1 means 0 1. So if you see clearly, we are using only 3 states. So this state and 1 comma 0 this state and this state, only these 3 we are going to use, only these 3 states we are using from the JK flip-flop. With the help of this combination, we are using this state and this state. Only 3 states we are going to use, but we are not going to use the remaining 2 states. We are not utilizing the remaining 2 states from this B flip-flop. Only 3 states that we are going to choose here. So when our clock is equal to 0 respect of the D, we are going to get memory. When clock is equal to 1, so B is equal to 1 means J is equal to 1, K is equal to 0. So Q is equal to 1, Q bar is equal to 0. And when B is equal to 1 means J is equal to 1 and K is equal to 0. So we are going to get 0 and 1. So 0 and 1. Only 3 states. This state and this state. Only 3 states we are going to use from JK flip-flop. With the help of this, we can insert small amount of rearrangement. This is called as the B flip-flop. So now I want to know what is this excitation table, state diagram and the characteristic equation. So you can see clearly I have already told you with this input we are changing output from Qn to Qn plus 1. See these are the 2 input variables. So therefore 0 0, 0 1, 1 0, 1 1. See if you want output to change from 0 to 0, we have to do d is equal to 0. If you want to change the output from 0 to 1, we have to do input as is equal to 1. If you want to change the output from 1 to 0, we have to do input as 0. And if you want to change the output from 1 to 1, we have to do input as 1. So you can see clearly this is called as the excitation table. So if I want to make it in terms of the state diagram, if I want to basically write in terms of a plot, you can see if I want to change the output from 0 to 0, I have to do d is equal to 0. If I want to change the output from 0 to 1, I have to do d is equal to 1. So if I want to change the output from 0 to 1, I have to give input as d is equal to 1. If I want to change the output from 1 to 0, I have to give input d is equal to 0. So if I want to change the output from 1 is equal to 0, I have to give input as d is equal to 0. If I want to change the output from 1 is equal to 1 to 1, I have to give d is equal to 1. So if I want to change the output from 1 to 1, I have to give input d is equal to 1. So you can see clearly, so this is the plot diagram that we are going to get from this table. This table is called the excitation table and this is called as the state diagram. So now we will discuss about the characteristic equation. I already told you, see for Qn, for basically for D and Qn, we are going to get Q of n plus 1. So therefore, for 2 inputs, D and Qn means 4 combinations we are going to get. So for these 4 combinations, we are going to get Q of n plus 1. So if you make an equation, if you make it came up in terms of Q of n and Dn, finally we are going to get Q of n plus 1 is equal to D, because we can see clearly from here itself, whatever this Q of n plus 1 is equal to D. See 0 0 1 1 0 0 1 1. So always Q of n plus 1 is always equal to D. So this is the meaning of D flip-flop. So whatever the input, same thing we are going to get in terms of Q. If D is equal to 1, Q is equal to 1. If D is equal to 0, Q is equal to 0. So D is equal to 1, Q is equal to 1, and D is equal to 0, Q is equal to 0. So whatever the input is passing through output whenever the clock is on, so this is called as the data flip-flop or D flip-flop. So now we are going to learn about the T flip-flop. T flip-flop means here we are going to, what is JK flip-flop, JK and the clock Q and Q bar, we are joining this J and K. So if you join these 2 terminals J and K, this common terminal we are going to call this as the T. So this, if you do arrangement like joining this JK and if you call this as a T, this is called as a T flip-flop. Just rearranging the JK flip-flop using some modifications. If you do some modifications like this, it is called T flip-flop. So this is equivalent to a T flip-flop, T, clock, Q and Q1. See, whenever the clock is equal to 0, in respect of the T, in respect of J and K, always we are going to get memory. I have already told you. Suppose if clock is on and T is equal to 0, so 0 0 means again we are going to get memory. And if T is equal to 1 means J is equal to 1 and Q is equal to 1, K is equal to 1, it is called as a toggle mode or resonant condition. So in a D flip-flop, we have used the 3 states. The remaining 2 states we are going to use with the help of this T flip-flop. So this is the thing that you always have to understand. So this is the important point that you have to keep in your mind. So this is the way that just we are going to do some modification to the JK flip-flop, then we got the B flip-flop and also T flip-flop. So just by joining these two things, it is called a T flip-flop. So clock is equal to 0 irrespective of T, you are going to get memory. So when your clock is equal to 1 means T is equal to 0 means D is equal to 0, K is equal to 0 means it's a memory. And when T is equal to 1 means T is equal to 1 and K is equal to 1, you are going to get a toggle mode or there is a one condition. So continuous variations of output from 0 to 1 and 1 to 0 continuously. So now let me tell you about the excitation table. So here for this input T, we want to be changing Q1 to Q of n plus 1. For 0 0, 0 1, 1 0, 1 1. So these are the combinations. For these combinations we have to see what is the input that we have to give. So if we want to change from 0 to 0, then we definitely have to give a memory. Memory means again 0. 0 to 1 means you have to give toggle is equal to 1. If you want 1 to 0 means you have to give a toggle which is 1. If you want to change 1 to 1 means memory which is 0. So we can see here this is called the excitation table. So if you want to change the output from 0 to 0, you have to give T is equal to 0. So if you want the output to change from 0 to 0, you have to give input T is equal to 0. If you want to change the output from 0 to 1, you have to give input T is equal to 1. So if you want to change the output from 0 to 1, you have to give input T is equal to 1. If you want to change the output from 1 to 0, you have to give input T is equal to 1. So if you want to change the output from T is equal to 1 to T, from 1 to 0, you have to give T is equal to 1. If you want to change the output from 1 to 1, you have to give T is equal to 0. So if you want to change the output from 1 to 1, you have to give T is equal to 0. So this is the excitation table and this is the state diagram. So now if you want to draw the characteristic equation, I will already told you for T and Qn. For T and Qn, try to figure out the Q of n plus 1. So for this T input, the output Q is changing to Q of n plus 1. So for T and Qn, two input variables means 4 combinations. Find the value of Q of n plus 1. And with the help of Q of n plus 1, try to figure out the relation between the T and Qn with the help of K-map. Then you are going to get Q of n plus 1 is equal to T of T XOR Qn. T XOR Qn is the equation that we are going to get. So this is the important point that you always have to keep in your mind. So this is the thing that you always have to keep in your mind. This is called as the characteristic equation. So now we are going to learn about the another important concept which is called as the constructing a desired flip-flop from the given flip-flop. So basically they are given some flip-flop. So based on this we have to figure out the desired flip-flop. So they are given some flip-flop. So based on this flip-flop we have to do some modifications to this given flip-flop and then we have to get the desired flip-flop. That is the meaning of this one. So there are some rules. You have to always understand this rules. Based on this rules only we have to design this one. So constructing the desired flip-flop from the given flip-flop. So we are going to give some flip-flop to you. So for this we have to do some modifications to get the desired flip-flop. So now first thing is there are 3 rules that we always have to keep in the mind. So if you follow these 3 rules, then you can get whatever the desired flip-flop from the given flip-flop. First thing, write the truth table. Write the truth table for the desired flip-flop. So like this, desired inputs comma Qn and then figure out the Q of n plus 1. So listen carefully. So first thing is you have to write the truth table for the desired flip-flop. Means what are the flip-flop that you really want, that you are really desiring to make from the given flip-flop. So write the truth table for the desired flip-flop like desired inputs comma Qn. So desired inputs and Qn, take this combination. So with this combination we are going to figure out the Q of n plus 1. So with this combination of desired inputs and Qn, so with this total combination, try to figure out the Q of n plus 1. Then for this Q of n and Q of n plus 1, figure out the input values of the given flip-flop. See, now what we have to do for this Q of n and Q of n plus 1, we have to figure out what is the input, what are the inputs which must be required for this input of the given flip-flop. So for this, for those Q of n and Q of n plus 1, figure out input values of the given flip-flop. So if you want to change the output from Qn to Qn plus 1, what are the input values must be required for the given flip-flop, we have to figure out. So for this Q of n and Q of n plus 1, figure out the input values of the given flip-flop. So now given flip-flop inputs is equal to, so now given flip-flop inputs is equal to function of desired inputs comma qn, desired inputs comma qn. Now forget the q of n plus 1. So now what you have to do, so now find the expressions for the given flip-flop inputs is equal to the function of desired inputs and q of n, and now forget the q of n plus 1. So whatever the given inputs are there now, so now for that we have to have the carbon of in terms of desired inputs and qn, and then we have to forget about the q of n plus 1 and try to get the relation of the for this given flip-flop inputs in terms of desired inputs and qn. So now with these expressions try to connect the circuits, then we are going to get the desired flip-flop from the given flip-flop. So this is a important point that you always have to consider. So if you follow these 3 steps, definitely you are going to build the desired flip-flop from the given flip-flop. The first thing is that you have to always remember is write the truth table for the desired flip-flop, which is desired inputs comma qn. From this you have to figure out the q of n plus 1. The second step is for those q of n and q of n plus 1, figure out the inputs values of the given flip-flop. And now given flip-flop inputs you have to write in the function of the desired inputs comma q of n, and now forget about the q of n plus 1. So if you do this one, then definitely we are going to get the whatever the desired flip-flop from the given flip-flop. So these 3 important that you always have to keep in your mind. So listen carefully. Write the truth table for the desired flip-flop in terms of desired inputs comma qn, and try to figure out the value of the q of n plus 1. And for those q of n and q of n plus 1, figure out the input values of the given flip-flop. And then in the given flip-flop inputs you have to write in the function of desired inputs comma qn, and forget about the q of n plus 1. So this is the 3 points that you always have to keep in your mind. So now you can see clearly, so this is given in terms of a diagram, you can see clearly. So these are desired inputs. So desired inputs and qn, write this all these combinations for these desired inputs and qn, write all the combinations. For this overall, write the combinations and try to figure out for this desired inputs, the qn is changing to q of n plus 1. So try to find these values. And now for this variation from qn to q of n plus 1, what are the inputs of given flip-flop that we need to figure out. Then now what we have to do, so now you have to find these expressions. In terms of desired inputs and qn with the help of k-nav, try to reduce and forget everything about this q of n plus 1 and try to get these values, these variables in terms of this and this. And now now try to do the circuit connection, then we are going to get the desired flip-flop from the actual flip-flop. So the first step is we have to make the desired inputs and qn, try to make all these combinations and try to figure out the q of n plus 1. And now the second statement is for this q of n to change to q of n plus 1, what are the inputs of the given flip-flop that are required we need to figure out. And the third statement is here, now forget about the q of n plus 1 and just try to find what is the expressions of these inputs of given flip-flop from the desired inputs and qn with the help of k-nav. So we are going to get the expressions and now try to connect the in a circuit diagram, then we are going to get the desired flip-flop from the actual flip-flop. So this is the point that you always have to keep in your So this table, if you remember, you can easily get the desired flip-flop from the actual flip-flop. So now let me tell you some important things here. See, JK to other flip-flops. So in the here they are given JK flip-flops, and I want to configure the JK flip-flop to other flip-flop. Then we are doing like this. See, if I want to configure JK to B flip-flop, and I want to for this JK flip-flop, we have to connect an inverter between J and K, and this common part we are going to assume as B. So we can see clearly from here the circuit, we have made the B flip-flop from the JK flip-flop by this connection. Similarly, I want to make, say from JK flip-flop, I want to make the T flip-flop. So we are given JK flip-flop. So with this connection, I connect the J and K together and I call this as T. So with this JK flip-flop, I made the T flip-flop with this connection. Similarly, JK to SR flip-flop. So we are given JK and now I want to make this as the SR flip-flop. Just connect this J to S and K2R. So this is called as the SR flip-flop. So therefore, if you connect J2S and K2R, this is called as the maybe SR flip-flop from the JK flip-flop. Similarly, I want to make the T flip-flop to other flip-flops. Suppose if I want to connect the T flip-flop, suppose if I want to make, if I want to configure the T flip-flop to other flip-flops. So I want to make T to JK flip-flop. So I want to build JK flip-flop from T flip-flop. So you can see here this is a T, this is the clock, this is the Q and this is the Q bar. So this is a T, this is the Q bar, this is the K, this is R. This is J actually, this is a J and this is the QR, this is A, this is a Q, this is the AND gates and this is the OR gate. So we are given here. So with the help of these three steps I already told, if you follow this one, we are going to get the connection like this, and if you connect something like this is called as a JK flip-flop. But from T flip-flop we made the JK flip-flop with this extra circuit connection. Similarly, T flip-flop to SR flip-flop. So I want to make the SR flip-flop from T flip-flop. Then you have to do some arrangements. In the three steps that we have followed here, we are going to get this is S, this is Q bar, this is R, this is the Q, this is the both are AND gates, and here is the OR gate. Same thing, same as the previous one. So this is called as the SR flip-flop from T flip-flop we made. Similarly, T to D flip-flop. So I want to make D flip-flop from T flip-flop. Same thing I have to do. And this is the T, this is the Q bar. So this is the D, this is the Q, this is the XOR gate. So if you follow the three steps I already told you, so we are going to get certain expression. And if you try to figure out, if you try to reconnect this one, we are going to get like this. So this is called as the, we made D flip-flop from the T flip-flop itself. Similarly, I want to make SR to other flip-flops. Suppose I want to make SR to JK flip-flop. So this is the SR flip-flop, it's a Q bar. So here I have to keep the AND gate, this is a J, the Q bar. Here there is a Q, K and this is Q. Both are AND gates will become like this. So if you follow those three steps, then we can make JK flip-flop from S flip-flop like this extra connection. So similarly from SR to T flip-flop. So if you want to make SR to T flip-flop, this is the SR Q bar. And here we have to give basically an AND gate, and common input is a T, and Q bar and Q. So if you do like this, we have made T flip-flop from the S flip-flop, SR flip-flop. Similarly, SR to D flip-flop. So I already told you, first you have to create an AND gate between this S and R. Then we are going to get this is called as a D flip-flop from SR flip-flop. Similarly, D to other flip-flops. So D to SR means, see, this is the D flip-flop, D, Q bar. Clock. So this is the OR gate we have to keep here, this is S, and this input we have to take from output of this one, which is Q and R. There is a NOT gate here. So this is called, if you do the arrangement in this fashion, so we have made the SR flip-flop from the D flip-flop. Similarly, D to JK flip-flop. So if you want to make JK flip-flop from D flip-flop, so this is the D flip-flop, D clock, Q bar. So there is the AND gate, J, Q bar, and there is a K bar Q, and here we have to give OR gate like this. So we have made a JK flip-flop from the T flip-flop itself. Similarly, we can say D to T flip-flop. D to T flip-flop means I am making T flip-flop from D flip-flop. Then is the D flip-flop, Q, D clock, Q bar. This is the T, this is the Q. So T XOR Q, we are going to give input to T. So this is basically we made T flip-flop from D flip-flop. So basically, if you follow those three steps I already told you, if you follow those steps blindly, you are going to get the desired flip-flop from the actual flip-flop they have given. So now, let me tell you some important clocking signals. See, this is circuit A, circuit B, circuit C and circuit D. So you can see clearly, if there is a straight line with the clock, it is called as the high level triggering. Suppose there is a small bar, you can say small knot like this, it is called as a low level triggering. And with an arrow like this, it is called as the, we can say, the positive edge triggering. Suppose there is an arrow with a small dot, it is called as the negative edge triggering. So this is called as the high level triggering, low level triggering, positive edge triggering and negative edge triggering. So these are the different types of clocks we can give here. So high level triggering means whenever the clock is equal to high, the circuit is going to get function. So low level triggering means whenever the signal is low, when the clock signal is low, the circuit is going to get operate. If you, this is called the positive edge triggering. So whenever the clock is having a positive edge, which is low to high, then only the circuit is going to get function. Otherwise, it is not going to function. Otherwise, it is going to stay in the memory state. Similarly, here, negative edge triggering means there is a not here with the arrow. So whenever a clock is going from high level to low level, so there is a negative edge triggering. At this condition, the circuit is going to act. Generally, inputs are going to pass through output, otherwise it's going to act like a primary state. So these are the important points that you always have to remember. So during this triggering only, it is going to, whatever the inputs they are going to, based on this inputs, the output is going to get vary. In the remaining time, it is always going to stay in the memory state. So this is called the high level triggering, low level triggering, positive edge triggering and negative edge triggering. Circuit A is called as high level triggering, circuit B is called as low level triggering, circuit C is called as the positive edge triggering, and circuit D is called as the negative edge triggering.